minutes for the participant, for the attendee to join us, and then I'm going to start this event.
Comincia a dire che c'è.
So welcome Mario Sanchez, welcome Professor Daniela Baglieri, welcome Professor Milone, welcome Dr. Juan Coronado, welcome Alfonso Carrillo, welcome Juan Pablo Rincón Duarte, welcome Johannes Gobler. I'm going to have to tell you that today, unfortunately, Francesco Rovense will not be joining us because of some personal problems. We hope that he's going to recover soon. You can find his contribution among the files that I shared with you all, his presentation, and also there is a very short book of abstract. And if you need to contact him, there is his contact on the presentation. So I think it's almost time to start our first forum of young researchers in energy and environment. Thank you, Professor Baglieri, for giving the welcome to everybody on the behalf of the University of Messina. And I want to thank the university for giving us the opportunity to do this event, and especially for sponsoring it, because so in this way everybody is allowed to join us, starting from the researchers to the students to the general public. So thank you.
Thank you, Emanuela. Thank you, Ida, and welcome everybody. And I'm very honored to be here just to give you my personal welcome, and also on behalf of Magnifico Rector, Professor Kutsokrea, is engaged in other institutional staff. So welcome here. And why I'm here, I'm very glad to be here to share this moment, but personally for three key drivers. First of all, it's the first of someone, so that's the first step of other, and I suppose I expect more event like this. The second reason, so that's the first of what? Of a platform of young researchers, so again, young people. And the young people are the fuel of the next generation, and try to shape also the research, and the research in what? In the topic. Your topic is really particularly relevant because you are going to discuss about energy, environment. So are the two big issues. So again, it's not only Europe, or especially in the uncertain period. So again, it's really relevant to give you, and I really appreciate the idea of Emanuela and all this effort. Thank you. We thank you, because we need all this energy. It's not thermal energy, it's human energy, because we need to reshape, to rethinking also our education system, and to rethinking also how can we collaborate, how can we do research, because the idea in how can we create value is in order to boost, how can we impact with our research the world, and the next future. Because when we tried, I'm trying to say that we are researchers, so we are much more focused on doing research, but probably it's time to thinking about how can we deliver the research for society in order to be much more impactful for the next generation, and also for the current period, because it's not just doing thinking about the future. Unfortunately, we are thinking about now, the current period. So the post-COVID is a phasing, is challenging also our ordinary thinking, also to do research. So that's why I'm very glad to open the first but not the last first forum on young researcher in energy environment. And being in Messina, unfortunately, we are online. I know that some philosophers say that we are on live, but again, I hope to welcome physically in the next future. And I invite you to share the idea also after this event, this workshap, and I'm very glad to be in touch with all of you. Again, thank you to all the participants. Thanks to the guest speaker. Thanks to Ida Milone. A special thank to Emanuela for the effort. And I wish you all the keep up the good work. Thank you again.
Thank you so much. Now I give the word to Professor Milone. Welcome to the meeting. She is going to be our moderator, and she is the head of the engineering department. So please go ahead.
I think I have to. Maybe not. Okay, let's go.
Ida.
Okay, can you hear me? Yes, great. A warm welcome to all of you, and thank you to Professor Baglieri, because it's very important for us having the support of our university on this important moment, this important webinar. That I agree with you, Daniela, that I hope it will be it's the first, but it will be not the last, but not only for this hot topic, but I think there are many hot topics in several areas that deserves to have such young people meeting together, sharing ideas, sharing results, sharing research, and to go ahead. Thank you to Emanuela for having the idea of this first meeting between young researchers working on thermochemical storage. And especially, I cannot be, I'm very happy for this because even if in this moment I'm the director of the engineering department, so maybe many of my energies goes to the department, all the department, but this is my research topic and that I have on which I work on, and I have worked on together with Manuela in the past. So it's a great moment also to me to have the opportunities to share with all of you the new development, and also to hear from you new idea, new way of thinking, a new vision maybe of on this topic. This topic join many expertise from materials to systems to economical aspects related with the possible scalable and for possible application. And this is a really hot topic, and the results are all over the world. I mean, there are many people sharing, spending energies on energy topics. It's exactly many energies involved. And as you know, as all of you know, using the energy of sun, which is a huge amount of energy, very economics and easy to, not really easy to use, but of course it's available for everyone, so no discrimination all around the world. using energy of the sun, it would be the real goal for the future. And now the new systems for example, solar thermic plants have reached really very, very interesting results, because approaching to 1,500 degrees C of heat taken from the sun, maybe several years ago was not even thinkable. But now it is a reality, and this will push up, I think, in a very, very fast way, the possibility to have a real use of this energy. But I think that could be time to start with our first speaker, and to start with discussion and with comparison of idea. And so if it would be, it's a pleasure for me to introduce our first speaker, and the keynote lecture will be of Dr. Juan Manuel Coronado. Thank you to be here. And first of all, I would like to introduce Dr. Juan Manuel Coronado. Juan Manuel is a senior researcher at the Institute of Catalysis and Petrochemistry of the Spanish Research Council in Madrid. He received his PhD in chemistry from the Complutense University of Madrid in 1995. He was a visiting scholar at University of Dundee, UK, under the Marie Curie program, and at Universities of Wisconsin and Pennsylvania State. He worked as tenured scientist at CIEMAT, Madrid, and as a senior researcher at IMDEA Energy in Madrid too. He published 148 scientific papers with over 7,000 citations and impact factor of 50. His scientific activities focused on catalysis for energy and environmental applications and thermochemical energy storage, and he has been responsible of several research projects. So the keynote lecture, which is titled Current Challenges of Thermochemical Storage with the Redox Oxide, deals with the really hot topic because metal oxides with redox properties are very, very useful materials for thermochemical energy storage. And especially when we speak at high temperature. And these are really required for the next generation of concentrated solar plants. However, the need for the systems with higher energy density and durability has prompted a significant research interest in these materials. And in parallel, it has driven development of other related processes, such as, for example, oxygen pumps. So therefore, this lecture will summarize the current states of the art of this field, and it will discuss the main challenges for the large-scale use of these systems. So, Dr. Coronado, please.
Thank you very much, Professor Milone. Thank you, Emanuela, and the University of Messina for organizing this. Okay, I will try presentation. Okay. It is okay. I hope you can see it. Well, as has been mentioned, my presentation is about the challenges of the thermochemical storage with redox oxides. This is the outline of my talk, and I'm going to speak a little bit about solar thermal energy. I will try to show you why it's important. Then I will speak about the thermal storage as a key component of these plants and tell you why they are a key component. And then I will speak about some of the research we have done with the redox oxides as materials for thermochemical storage. And finally, I will give you some very brief perspective of the new application and new materials that can be investigated in the future. Okay, I don't think I need to convince you that renewables energy, and in particular solar energy, is very important for the future. But one question we have to answer first of all is if we have enough sunlight for power our systems. Well, the thing is the numbers are here. We have like 430 exajoules per hour arriving to the Earth. So this number is really huge, but to give a better idea of what that represents, I can show you here this square in the Sahara Desert is part of the land that we'll need to use for powering the whole world. So this is actually a little bit of cheating because this is assuming that we have 100% conversion. That is not possible, obviously. So we have to multiply this square for several times, maybe 6 times, and it's obviously a huge amount of land, but is compared with the whole surface of the Earth, and take into account that this is compatible with some other application. So we may say that sunlight is a feasible way of powering our future. So regarding the technologies, we have 2 choices. Photovoltaic PV is almost 2% of the, is already almost 2% of the generation of electricity, and is increasing efficiency and reducing cost. But concentrated solar power, thermal solar energy, is less, is 0.5%, but still a very interesting technology and can be complementary to the PV, as we'll see. For in the case of the concentrated solar power, that is the technology I'm going to speak today, there are several possible ways to get this concentrated power. But basically, for commercial application, we had 2 of them. One is the parabolic throat collectors here, and the other one is the central receiver with a tower, like this one huge plant. I think it's the Solana one in the southwest of the USA. Well, these commercial plants are working in around 600 in general, while in the case of the parabolic throat collector are working at lower temperature, around 300. But there are plans for having future technologies that will be working at much higher temperature, above 1,000 degrees. So regarding the deployment of this technology, you can see here in the blue that there is a lot of this kind of generation in the US, in Spain, in Morocco, India, China, South Africa. But there are also plans for having additional plants in the future in Chile, in other parts of Europe, and also in Australia. So if you want an example of what is the impact of this technology in the whole energy mix, you can see here one example from the last summer in Spain. This is for the production in this date. And you can see that the share, this in red, of the solar thermal was about almost 6% in the peak moment. This is not too much probably, but it's already significant. So I think this is an important contribution. And one thing I would like you to notice is that this energy is not only produced during the noon, during the central hours of the day, but it's also produced during the night. Why is this? This is because we have a storage. That's the important point we are discussing here. Obviously, we can use batteries for storing electricity, and this is perfectly technologically possible, but it's quite expensive. It's not the same that to having lithium battery for our cell phone that having a huge amount of batteries for storing the electricity we are producing. So this is the advantage of having the thermal systems, that we can store more cost-effectively heat than electricity. And this is one of the advantages of the concentrated solar power. So in that way, we can use the energy that we are producing but not using, because the demand is low during during noon, and we can use that power in the evening. And obviously, we can provide some stability to the system, and we have certain advantages of doing that. Obviously, there are several plants in the world, like this one in Solana, that is very large in the United States and has 6 hours of storage, so it can work after sunset, as I told you. Okay, there are several types of heat storage. We can use sensible heat, that is a mature technology, and actually is the one that is in use right now for these plants, and it's based on the difference of temperature. And in particular, the plants are using molten salts like potassium nitrate. We can also use the heat associated to the change of phases, like latent heat. This is a technology that is very interesting because it can increase the density, but it's for high temperature application, it's not so adequate. So in general, we are more focused on thermochemical storage systems that are less developed, but they are interesting because they can prevent the heat losses and it can get a higher energy density. So this is one of the important things we are going to discuss today. Obviously, we need to integrate these systems in the plant, so we need to have like a double circuit for the heating. One is taken to the power block where the electricity is produced, and the other, the overproduction is taken to the thermochemical storage unit where it is charging this material. And then when we don't have the light of the sun, then we can reduce this heat using the secondary circuit to power the block and to keep generating electricity. This is an example of this huge reservoir of solar salt they are using in some of the plants right now. And these salts can be used at up to 600 degrees, probably a little bit less than that, because after that, at temperatures higher, you start to decompose and you start to have problems. So as you can see, this technology in the plants is a combination of several elements. We need to store materials, that is the focus of today. But we also need a reactor that at the same time is a heat exchanger. We need a system integration in order to have a smooth operation of the whole system. Okay, what is going to happen in the future? Well, there is a lot of investigation in new thermodynamic cycles that are going to operate at higher temperature. The reason for that is that when we increase due to the Carnot limits, if we increase the temperature, we increase the efficiency, so we can even get closer to 60% of thermal conversion efficiency. That is huge efficiency. But for that, we need to use a high temperature. So right now, we are centered around 600, and in the future, using different thermodynamic cycles, we'll be able to go higher than 1,000. And for that, as I told you, we cannot use the solar salt, so we need an additional materials for storing the energy. So that's the reason, because there is a lot of research at this moment regarding the materials for the thermochemical storage. So what do we need for a material to be good for this application? Well, obviously we need a high energy storage density. We need stability, chemical and thermal. We need a rapid kinetic, so we need a fast charging and discharging. And because we are going to use a lot of material, a huge amount, several tons. So we need something that is cheap and abundant. And if possible, we would like also to have some high thermal conductivity, some good mechanical properties, low toxicity, low flammability, low corrosion, etc. So one important thing we need to see is the thermodynamic properties of these materials. Here we have several samples of several oxides that we can use for this application. As you can see, they have different temperatures for this reaction to proceed, and they have also a different slope in this plot of the free energy as a function of temperature. So in the case of the steeper slope, we are going to have a higher impulse, a higher driving force for performing these reactions. So thermodynamics is very important, as you will see in the next talks. So this is how it works, the system. We have first, we are having probably an inert gas or even air in some cases through the system, and we have the heating of the sun, and we are going to release some oxygen, and we are, in this particular case, we are going to transform this oxide, the manganese 2O3, into manganese 3O4. And if we want to recover the heat, what we do is the opposite reaction, and then we provide the oxygen, so that is taken by the solid and is releasing the heat. Well, this, if you want to see the chemical equation, is that one. So we are changing, in this particular case, the manganese oxide 2O3 into the spinel, the 3O4, and we are getting this enthalpy. Well, I choose this sample because it's one of the materials I've been working in the collaboration with Alfonso Carrillo a lot, because this is it provides a good balance between the cost and the thermodynamical properties. But at the beginning, we realized that this is not perfect. We have several problems. Sorry. Hello, can you hear me?
Yes, now yes.
Okay, I don't know if I can share my presentation.
Okay.
Okay, here we are. Sorry about that. Okay, we are here. So I was telling you that we have the charge, and we are releasing oxygen, and then if we cool down, we again recover the oxygen in air, and we go to the beginning. But as you can see, these two processes, charge and discharge, they have a gap in temperature, and this is not good for the efficiency. So one of the things we want is reduce this gap. One important aspect that we have also to improve is the stability of the material, and we have managed to improve a little with changes in the morphological configuration of these oxides. But you can see
that
yes.
Sorry, but we cannot see your presentation.
Oh, sorry. Okay, can you see that?
Now, yes. Okay, it's okay. Perfect. Please.
Sorry about that. Okay, I was speaking about that. So we had two problems: the gap in the temperature gap between the charge and discharge, and we have the low stability that is losing the rate, is decreasing with time of operation. So in order to improve the material's properties, what we did was using iron doping. We tried another doping, but iron is the best. And you can see here that if we increase the amount of iron, we have a narrowing of this gap. So it's reaching a certain point where we cannot get it better. But at around 20%, that is, we have a quite important reduction. And more importantly, this is done with an increase in the energy we can store in the material. So we have a more than 20% increment in the density of energy. Regarding the stability, that's a huge progress, because if you compare the material with without any doping, here you can see here that the reaction of recovery the oxygen after 29 cycles is very slow. It's taking almost 2 hours, but in the case of the material that is iron doped, you can see that it takes only a few minutes. So we have a great improvement. You can see here also what is happening with when we run 75 redox cycles up and down. We are taking and releasing oxygen. They are everything together. So you can see up and down, and you can see that this is fairly stable, although we have some drift in the baseline, but in the end, we have the same properties of the material, so we don't have any degradation. Apart from the pure manganese oxide, we can use another mix oxide like the Espinel, for example, this one with copper, that is providing certain advantages in terms of the rapid rate for the recovering of oxygen, but it's not huge. I mean, this material is not either perfect because it has the energy density is not great. There is also some possibilities that we are thinking about combining these materials in composite. This has been done before, not with oxide, but with carbonates. That is also a material for thermochemical storage. So I think there is here a certain field for improving materials. Before I finish, I would like also to mention that these redox oxides can be used for other applications. One is the oxygen separation, because as I mentioned, so this material is taking oxygen and then is releasing, so we can take advantage of that, and we can use that for purification and having a pure stream of oxygen. This can be powered also with the sunlight if needed, so it can be a process that is done with a low, with renewable energy. And we can also take advantage of what is called the chemical pumps. That is a way of shifting the balance, shifting the equilibrium for the production of solar fuels. So we can use that is taking the oxygen, although it's not active for production of solar fuel. And this is taking the oxygen in excess, so it's reducing the pressure and shifting the equilibrium. In that way, we can get an additional efficiency. So I think this is something that is going to be interesting in the next years to improving this material, this combination of two processes, let's say, thermochemical storage with the solar fuel production. So basically, all I have been speaking right now, up to now is about the stoichiometric oxides, but we can do a lot of things also with non-stoichiometric oxides, as it will be shown in the next presentation by Emanuela. So this is another thing that can be really interesting for the future, but I'm not going to speak about that. Just want to finish, just giving thanks to the people involved in this work, like Alfonso Carrillo and also Emanuela here in Madrid, and all the people in the Catalysis Institute in Madrid. And thank you to you for attending to this workshop. Thank you. I'm sorry about the technical problems. I hope you could follow the presentation.
Okay, thank you to you, Juan. No, it's no problem. You know, it's typical during, especially the first presentation,
Yeah.
maybe. So thank you for your interesting talk. And first of all, I would like to ask to if there are some questions, and you can click on the hand you see in the upper part of the screen. If it's not, I don't see. Okay, if it's not, I would like to ask you, Juan, about the mixed metal oxide, magnesium and iron oxide.
Yes.
Okay, could you please add something about the structure of the best performing materials? I mean, it's a solid solution, or what else?
Yeah, it's a solid solution. In this case, is this byte is it keeps the structure of the original manganese oxide when you have the doping. One of the advantages of the iron is that it's quite close to the manganese in terms of size and properties. So solid solutions are easy to form in this case. So in this particular case, we are introducing the iron without any change in the structure, but it's keeping the initial despite the structure, the manganese 203, and it's going to the spinel, that is the manganese 4. In that case, when we have a lot of iron, we may have a mixture of 2 spinels, 1 cubic and another tetragonal, if I'm not wrong. But we're basically keeping the structure.
Okay, so it also means that the two kind of spinel behaves differently, of course, in terms of
yeah, at certain point, I think we didn't go further than 40% because we didn't see any further advantage of increasing the amount of iron. But yeah, probably you start to have a certain points mixture of phases that maybe it's not so good for the performance because in the end can give you some troubles for stability of the system.
Okay, thank you very much. Thank you again for being here with us. And so let's go to the second speaker. It's Dr. Emanuela Mastronardo.
Emanuela Mastronardo, just a brief introduction.
So Emanuela Mastronardo received her PhD in Engineering and Chemistry of Materials in 2016 from the University of Messina. During her doctoral studies, she has been visiting researchers at the Laboratory of Advanced Nuclear Energy of the Tokyo Institute of Technology. In 2017, she received the Marie Sklodowska-Curie Individual Global Fellowship that allowed her to develop her research project named CESPER, Solar Energy Storage Perovskite, as a postdoctoral researcher at the Materials Science Engineering Department of Northwestern University, USA, and at the Institute of Catalysis and Petrochemistry of the Spanish National Research Council, Spain, for the past 3 years. In her talk on doped calcium magnesium oxide for the thermochemical heat storage from concentrated solar power plants, she will present the results of the CESPER project from the materials development to the lab scale reactor tests. Please, Emanuela.
Thank you, Professor Mirone, for the introduction. I'm going to share the... Okay. Can you see the screen?
Yes.
Okay, perfect. So I'm going briefly to describe in what consisted the CESPER project. As already said, solar energy storage perovskite that was developed in collaboration between the ICP CSIC, Northwestern University, and the INVEA Energy Institute. In this project, it is proposed perovskite redox reactions for thermochemical heat storage application, more specifically for storing it coming from concentrated solar power plants. And in this kind of systems, the heat is stored during the endothermic reduction, and it is released during the exothermic reoxidation of the materials. The redox systems, the non-stoichiometric perovskites redox systems release oxygen in a broader temperature range with respect to stoichiometric reactions in which, like for example, in case of the binary oxides, in which the reaction occurs at a very specific temperature. And the main contributions, so the total heat storage capacity is given by two different contributions, the chemical heat and the sensible heat. Sorry, okay. So one of the key requirements for the materials to be ideal candidates for thermochemical heat storage is to have very high energy storage density, of course. And as we can see from this question, it is important to have not only high reaction enthalpy, but also a large reduction extent. However, in reality, a high reduction extent is associated to small reaction extent, since it is directly connected to the energy that is necessary to see into the material. Between the reaction enthalpy and extent in order to find a good candidate material. So one of the main advantages of using a redox reaction system is the possibility of tuning the thermochemical behavior through A-site and B-site doping. And for this study, we decided to investigate calcium manganese oxide because it's made of earth-abundant, inexpensive, and non-toxic element. And as already explained in Juan's previous talk, those are fundamental characteristics for the materials to be competitive in the market. However, these materials present a main limitation. It decomposes at temperatures above 1100 degrees C and for PO2 below 0.008 atmospheres. So this is going to limit the operating temperature range of the materials. And in this study, we proposed several actions: the B-site doping with iron, A-site doping with lanthanum, and also the co-doping with iron and lanthanum. So the first research objective of this study consisted into the identification of candidates materials and their screening with TGA DSC analysis in order to determine which could be the possible suitable compositions for this application. And we ended up with this list reported in the table, in which we have 10% and 30% iron doped and lanthanum doped compositions, but also 5% and 10% co-doped materials. Those selected oxides were fully characterized starting from in situ up to ex situ X-ray diffractions, up to the determination of the compositions through ICP OES and EDX analysis, and also their morphology through scanning electron microscopy. The second research objective of the project was the evaluation of the thermochemical behavior of these materials. So for this, we analyzed the materials through TGA DSC analysis coupled with PO2 sensors by running the cycles that I reported here in this graph. So we reduced the material up to a selected reduction temperature and then reoxidized back up to the selected discharging temperature under several different PO2, from the most reducing to the most oxidizing one. Using proper conditions for the materials to be in the equilibrium conditions during the cycles, in order to use the Van 't Hoff approach for the evaluation of the thermodynamics. So we basically extracted the enthalpy and the entropy of the materials, which were unknown, from the Arrhenius plot that we obtained from the delta T profiles that we got from TGA analysis. So I'm going to briefly show you some results. So we first check the stability of the materials, and with respect to the calcium manganese oxides, which showed decompositions into Radenstadt paper and the spinel structures and the most reducing conditions that we used, both in the XRD and TGA analysis, in which basically the material, the mass was not able to be uptaken back. All the doped compositions, with the exception of the 30% iron doped compositions, were perfectly able to uptake back the mass, as you can see from these graphs, under the most reducing conditions studied. And we determine all the delta T profiles for all the materials. And here I just briefly reported the one related to the co-doped samples, just to show you how the delta T profiles look like. And we could see that the heating and the cooling profiles are basically identical, indicating the complete reversibility of the reaction, and also the fact that the materials was under equilibrium conditions during the overall analysis. If we compare the thermochemical behavior, the reduction extent of all the compositions, we can see that basically, regardless of the PO2 that we use, the compositions, the oxide containing containing lanthanum, reduces significantly the reaction extent as the lanthanum content increases. While in case of the iron doped samples, it is possible to observe that that there is a significant release of oxygen well below the undoped materials, so for lower temperature, and this amount increases as the iron content increases as well. While in terms of the enthalpy, we can see that the reaction enthalpy is slightly increased in the case of the 10% iron doped composition and slightly decreased for the 30% iron doped. While for all the materials containing lanthanum, the enthalpy of the reaction is increased even significantly. But if we look at the thermochemical storage capacity that was evaluated at under the most reducing conditions of 1200 degrees C and 0.008 atmospheres, we can see that the CMF91 is the best candidate materials for showing basically the larger its storage capacity of around 350 kilojoule per kilogram. And it is also able to store the heat in a wider temperature range with respect to the other candidates, while the 30% lanthanum doped composition shows the poorest one. So we selected this candidate, this material, for testing its cyclability over multiple cycles, and it can be observed how this material is perfectly stable along 16 cycles. And we determined the total heat storage capacity considering the two contributions of chemical and sensible heat. That is about 984 kilojoule per kilogram. So it offers a really good heat storage capacity, and we decided to use these materials for laboratory scale reactor tests. So we prepared the pellets mixing the CMF91 powder with different amounts of carboxymethyl cellulose, and wet the powder with a few amount of water so that we can create a plastic compound that could be easily extruded through a die of 0.03 millimeters. And the extruded compound was cut into pieces of 1 centimeter length, and the pellets were sintered at 1100 degrees C under static air in order to decompose the carboxymethyl cellulose. And tested the pellets into the laboratory scale facility that is reported here in this figure, which mainly consisted in an alumina reactor and a furnace, And the exhausted gas were analyzed through MicroGC analyzer, and several cycles and several reduction oxidation cycles were run. This is a typical example of a program temperature that it was run. And several experimental conditions were investigated. We changed the ramp rate, the flow rate, and the PO2. We selected 5% containing carbon methyl CMC containing pellets that left after sintering a porosity of 55%. And this is the result. Just for sake of briefness, I'm going to show you just few results. This is the profiles that we obtained from the reactors, and the black line is the TGA analysis. We can see the profiles basically almost overlapped, and this is a quite exciting results, considering that we moved from a sample mass of 500 milligrams to a sample mass of 50 grams into the laboratory scale reactor test. So in conclusion, I would like to say that the doping is fundamental for improving the stability of the materials, and it can be easily used for tuning the thermochemical properties of the materials, starting from the enthalpy up to the reaction extent. And we identified these materials, the CMF91, that offers a good heat storage capacity of 984 kilojoule per kilogram, and it operates in a very broad temperature range, that is 400 and 1200 degrees C. So, and this project has already been said, has received fundings from the European Union's Horizon 2020 Research and Innovation Program, but it also has been partially supported by the US Department of Energy. I really would like to thank the project supervisors, Dr. Coronado and Professor Susina Haile, that is going to be the second keynote speaker of this workshop. I would like to thank also the collaborators, Dr. Jose Gonzalez, who is the head of the high temperature processes unit at IMDEA Energy, Mario Sanchez for his help with the laboratory scale reactor test at IMDEA Energy, and also Shin Kian at Northwestern University. And thank you all for your attention. If there is time available, I will be glad to take some questions. And I think I can stop.
Okay, thank you, Manuela. Yeah, yes, we are perfectly in time. There are some questions. No? Oh, I was practically astonished by the complete overlapping between the TG results and the reactor tests. Because which is the thermal conductivity of the material, and no temperature gradient.
Yes, so we really studied hard to find the proper way of analyzing this material, and Mario Sanchez helped me a lot with this test. And I have to say that the length of the bed was, so we studied considering the length of the bed, the porosity of the bed, and also the fact that we used also the same porosity of the pellets that we use in the TGA and in the reactor test pellets that we used. Also, I wasn't expecting this. We have to really check in the length, along the length of the bed, within the with the proper several thermocouples in them. But the results are very promising, considering the oxygen evolution profiles that we got. So it was a very exciting result, I have to say.
Okay, there is a question, and the question is, what is the storage energy density of these materials? From the audience.
Okay, so the storage energy density of this material, it was 984 kilojoule per kilogram of material. Evaluating in terms of volume, it's gonna be slight. I don't have the number here, but we evaluated it, and it's a large number as well. So it's in the order of the megajoule per cubic meter. So
okay, there is another question. Okay, what triggered the choice of lanthanum and iron as dopants and A and B sites respectively from Matthias Appote?
Okay, so it was very interesting, the fact that it wasn't still not investigated yet, the role of the iron, which has a different oxidation state with respect of the manganese. And I was interested in knowing how this would affect the behavior of the material. And there are ongoing some analysis related, some data analysis elaboration with Zane and Dexaf's analysis. And considering the lanthanum, we selected the lanthanum because it was known that for other systems, it was already observed an increase of the reaction enthalpy. So we were willing to understand how much we could calibrate basically the dopant amount in order to have a proper its storage capacity into the material, meaning balancing the reaction enthalpy and the reaction extent, because as I said, they are both linked together and they cannot increase both together.
There is another question from Wilson George. Thank you. Our great talk, Emanuela. I'm reading what is written on the chat. Are you able to provide further information on the kinetic targets for these non-stoichiometric oxides for thermochemical energy storage?
Okay, so finding kinetic targets, it's gonna be difficult because it depends on the application point of view. And so we need to, so that's why this forum also comes from. It comes from the fact that we need different skills. We need different, everyone has to, we need to find out a way to moving from the basic research, so from the material point of view, to the application. So we need to find a way to connect the application to the material as well, to the basic research as well. At least that's my opinion. Otherwise, it's gonna be just just basic research and nothing else. So we need to find the way to the link.
Okay. No more questions. So thank you, Emanuela.
Thank you.
So we are on, and the next speaker is Walter Lombardo. Is here? Yes. Okay, great. So a brief introduction of Mr. Walter Lombardo, who received a master's degrees in energy and nuclear engineering at the University of Palermo, Italy, in 2018. Currently, he is a PhD student in mechanics and advanced engineering sciences program at the University of Bologna in Italy, and a research fellow at the National Research Council Advanced Technologies for Energy Institute Nicola Giordano here in Messina. His scientific activity mainly focuses on the development of advanced technologies for thermal energy conversion and storage and tree generation. In his talk, Adsorbed Cold Storage for Mobile Applications Design and Preliminary Tests, he will present his research activity on the design and characterization of cold storage compact systems for mobile refrigeration applications. So, Walter Lombardo, please.
Okay, thank you for the introduction. Okay, I'm going to show the presentation. Okay. Can you see the presentation?
Yes.
Okay.
Can you please enlarge a bit?
Yeah, okay.
Okay.
So, okay, thank you. So, I will talk about our research topic about adsorption cold storage for mobile application. And I can start with a scenario. So nowadays, mobile air conditioning and refrigeration are solely based on vapor compression systems. So the problem is the application of and the use of refrigerants like HFC. So the problem of CO2 emission is a current challenge to be solved. So a solution can be the efficiency improvement of such systems with the recovery of waste heat for cold production. So we can consider alternative systems like adsorption chillers or cold storage systems that can be a solution because they can help the phase down of these refrigerants. They can reduce the fuel consumption of the vehicles or mobile applications, and consequently the environmental impact. So the idea generated by internal combustion engines can supply thermally driven technologies in order to provide refrigeration for transport. As you can see in the figure, we have a small van with a refrigerated compartment. Maybe you can imagine application of goods like food or medicines or other applications. So we can consider two phases in which during the movement of the vehicle, the taken from the engine is used to recharge the cold storage system located near the compartment, and during a stop, the system is discharged to generate the cold necessary to maintain the low temperature inside the compartment. So this is the main idea. Now, I will talk about our study about the technology. Then I will present the lab scale prototype realized and developed in our laboratories with a complete description of main components of the system. I will show you results of our experimental tests, and finally a discussion and conclusion about the study. So I start with the technology. So you can see the thermodynamic cycle. We have two phases, as I told you in the previous slide. The charge phase. So we have the first part of the cycle, okay, in which the heat taken from the engine is used to charge our storage. And after a certain time, we can use this heat and release to do the second part of the second phase, so the discharging phase, to produce cold. There is the heat exchanged at the evaporator. So this is the technology. This thermodynamic cycle is reproduced with a prototype that is composed of an absorber and a phase changer, as you can see in the red square. Okay, and it's connected to a testing bench in our laboratories developed to simulate the operating conditions. Okay, there are also a fluid distribution system and electronic for monitoring all physical parameters inside our systems during tests. The advantage of the system is that it's thermal losses free, so we can use it stored when we want. So I will talk about the absorber. We designed and sized this component under constraints provided from an industrial company that provided constraints of a real component. So we designed the absorber sizing with for 25% of the full capacity. And we tested two different types of absorbers. The first one is a composite absorber, characterized with an aluminum heat exchanger with flat tubes, with a coating with a Pharmazid Z02. And the second one is a pelletized absorber with a finned heat exchanger with aluminum tubes filled with grains of the same absorbent material. About the phase changer is characterized by stainless tube with copper fins. Okay, it is designed with a nominal power of 3.5 kilowatt. And as you can see, also the vacuum chamber inside where it's located is also made by steel. Okay, about the testing bench, as you can see, we have a cold tank and an hot tank. It's characterized with the possibility to simulate all operating conditions of our system. It's provided with a 16 kilowatt electric heater with a maximum temperature of 95 degrees. Okay, we can simulate a low temperature ranging between 0 and 20 degrees, and a medium temperature ranging between 15 and 50 degrees. About test, we can see the assessment procedure description. We considered the following key indicators to evaluate performance of the small storage: the average discharge power and the stored energy for mass unit. Testing protocol has been used for all tests and fixed and studied previously in other works, and it was used for both absorbers tests. So you can see in the slide a theoretical trend of temperatures during a typical test. So you can see in the left of the figure, we have during the charging phase the temperature of desorption is ranging between 80, 85, and 95 degrees. Okay, and during the discharging phase, we have a temperature inside the evaporator fixed between 10 and 18 degrees. So you can see also the switch between the two phases in the figure. So this is the real, a real typical test. You can see the temperature trends also both the phases during the charging phase and discharging phase, and you can see the useful effect during the discharging phase. So is the difference, the temperature difference at the evaporator, and it's about 10 degrees. So it's our useful effect to produce cold from the heat provided by the engine. This is the diagram and in which power and energy trends are showed. In the right part of the diagram, we can see about power, initial peak power, and after that the power goes to zero after a certain time. About the energy, we can see the trend, and finally we can evaluate the storage capacity. Then in this case is more or less 350 watt-hour. So we carried out a full characterization of both absorbers with more or less 250 total tests, and we achieved an average power during the charging phase up to 520 watt with a theoretical energy more or less of 600 watt-hours. So it's an interesting fact because it demonstrates the feasibility of this solution. About the two absorbers, so the composite and the pelletized absorber, results showed about a comparison of these two different types. We can see in the first diagram, this one, okay, the power versus the time. For the composite, we can see an initial peak power, it's 2 times the pellet one. Okay, but the process is very quick. It ends at more or less 1,000 seconds, while the pellet one is more constant, and it ends at about 4,500 seconds. Here we can see the trends of discharge power versus the condensation temperature, and also the specific energy, to make a comparison between the two solutions. So we can see the composite presents better performance in the range of between 27 and 35 degrees as condensation temperatures. So it can be taken as the best solution, and also for the specific energy. In conclusion, so the realization of testing of these different types of cold storage can reveal promising opportunities about this application, because tests showed that prototypes are able to store up to 600 more or less watt-hours of power, with an average power ranging from 200 to 800 watt with an energy efficiency of 0.3 for the operation in the selected conditions. So the study demonstrates the feasibility of this application to the refrigeration and the mobile application, and further improvements and optimization of the system has to be realized in further works. For the information, you can see also the paper we wrote, and you can see if you want. Thank you for the attention. I want to thank also my research groups and my supervisor. And it's a pleasure for me to be here to present my work. Thank you.
Thank you, Mr. Lombardo. So there is a question launched already on the chat. It's from Artem Nikolin. So I'm going to read it. The absorption refrigerators are bigger and are heavier than vapor compression ones. Moreover, the efficiency is lower. Did you perform life cycle analysis of the system you propose in comparison to the commonly used ones?
Okay, not yet, but life cycle analysis we are evaluating to do this kind of analysis, but in the main objective of our study in this moment is the optimization of this component of these systems, also for materials and components for this topic. But life cycle analysis will be performed and carried out for sure. Yeah.
Thank you.
I would like to ask you a question, which is more general actually, but I think it's still interesting to know which you think is going to be the impact of your study on the market scale, considering the costs that are related to this additional component that you're going to add into the vehicle.
Sorry, can you repeat the last part? I didn't understand.
I mean, what kind of impact are you going to expect to have on the market scale? This additional component that you're going to include in the, you're proposing it for vehicles, correct? So this is going to have an impact in terms of cost, correct?
Yeah. I think yes, okay. Because the trend about this solution is quite positive, and but the technology is not at mature point of view. But I think it will be a good impact in the market for this type of solutions. Also for the phasing out of common and typical refrigerant.
Okay.
Okay.
So you're expecting a high cost-benefit ratio, correct?
I think yes. Also for from an environmental point of view. Yeah.
Okay. There is another question from Johannes Grubel. Does the system require an internal combustion engines, or is there also enough heat available in battery electric bikes?
Oh, maybe you don't hear me. There is another question. Okay, sorry. There is another question from, I will get it again, from Johannes Goebel from DLR. The question is, does the system require internal combustion engine, or is there also enough heat available in battery electric vehicles?
Okay, it depends by the temperature of the charging phase, because we need temperature ranging between maybe 70 to 90 degrees. So the date source it can be whatever we want, not only an internal combustion engine, but an heat source with a temperature ranging between these constraints to supply the absorption storage during the charging phase.
Is it okay for you, Johannes Goebel?
Yes, thank you. I was just wondering because usually people say that we need in electric cars we have problems with heating the vehicle,
Yeah.
so there's less heat available, I thought, in electric vehicles, and that's why I asked this question. That's okay.
Yeah. Okay. So thank you again to Walter Lombardo. Thank you very much.
Bye.
And so the next speaker is Mr. Juan Pablo Rincon Duarte. Okay, welcome. So Juan Pablo Rincon Duarte, a brief introduction, received his master's degree in renewable energy systems from the Technical University of Berlin. And since 2018, he is a PhD student in mechanical science and engineering at the Institute of Solar Research of the German Aerospace Center, DLR. At DLR, he is involved in the project Calypso on calcium oxide looping through solar energy. So in his talk, he will present the latest results on the solar rotary kiln for thermal energy, for thermal storage application. So please.
Okay, thank you very much for this introduction. So, yeah, at the beginning of my presentation, I would like to explain why am I talking about a solar rotary kiln. Then I will present some results that we obtained during an experimental campaign using this solar reactor to do the thermal reduction of metal oxides. And in the end, I will report the work that we have been doing on the reactor to adapt it for running other thermochemical processes where I'm doing my PhD. So this is the diagram of a cycle that we analyzed in our institute. We were looking to incorporate the thermochemical storage using metal oxides in a solar tower plant system. So here, basically, we have a system with two storages. The metal oxide is taken from the cold storage and is brought up to the tower, and there the reduction step takes place, and then the metal oxide reduced is stored at high temperature, and the idea is to do the oxidation of this metal oxide in a separate reactor in times without solar radiation, using air as the reactant, and with the hot air to further produce electricity. So in this project in our institute, we had several material requirements, and one of the important ones here was to have a material with low environmental impact. And after analyzing different materials, we selected an iron manganese oxide to run our cycle, and we did the thermal reduction step using a solar rotary kiln. But okay, why a solar rotary kiln? So here I have listed different reactor concepts that we can use to run continuous solid gas processes. But here I have to mention that there is not like a best reactor for all the processes. When we select a reactor, this selection process depends on the material properties, the process conditions, and of course the chemical reaction. But today I'm talking about the rotary kiln, and this kind of reactor has several advantages. For example, we can handle a wider range of particles from micro to millimeters. Also, there are a lot of experience using these reactors at large scale processes, like yeah, it's the case in the cement industry where the clinker is produced in big rotary kilns. And also for solar applications, this reactor concept allows us to implement the direct heating of particles. And this is important because, for example, if we have inside the reactor one material which sticks to the inner wall of the reactor, and if this material is heated externally, so after some time, this material will create kind of additional thermal resistance, and then the temperature needed to heat the particles inside will be higher. So this is a picture of our solar rotary kiln taken during this campaign using the iron manganese oxide and in the solar simulator in Cologne. And here basically we have the material here inside this hopper, and it is brought inside the reactor using a screw feeding system. And then because of the rotational movement here of the crucible, and also because of the inclination of the kiln, the material will continue moving to the front, and then the material will leave the crucible and it will end up here in the storage. This part of the reactor can rotate while the front part is fixed. And here we have the aperture region where the solar radiation enters. And also the gases taking part in the reaction or evolving from the reaction can be taken out from the backside of the reactor. If we have a look at the inner side of the reactor, we can observe here the crucible more in detail. This blue part is insulation material that we put in order to avoid thermal losses. And we put also several thermocouples here along the axial direction of the crucible to have the temperature profile of our reactor. And in our experimental campaign with this iron manganese oxide, we had a material which particle size was between 2 and 3 millimeters. The mass flow that we use was about 9 kilograms per hour. And for this material, we had a reduction temperature of 1050 degrees, but we had to be careful because if we overheated the material over this 1100 degrees, the material deactivated. So in our experiments, we reach a maximum temperature of 1058 degrees. And for that, we use 6 lamps of the solar simulator, which is about an incident power of 8 kilowatts. Here in this graph, we can see the signals of the thermocouples inside the crucible, which are these colorful lines. And on the right side, we have the signals of the oxygen sensor that we have for the gas flow, as well as this black line is the mass flow. So we started the experiments turning on the lamps step by step. in order to avoid a thermal shock on the crucible. And after we reached the reaction temperature, we started the feeding of the material, which is this black line here. And some minutes later, we reach steady state conditions with the reactor. And if we take a look here at this, at the signal of the oxygen, after some minutes, we observe that the oxygen concentration in the gas flow increased. And here, that was an indication that we were already performing the reaction. We did several experiments, and we could demonstrate the feasibility of this reactor to run this continuous process. But now we are working on the adaptation of the reactor to run other solar thermochemical processes, as it is the case of the solar calcium oxide looping cycle. And here in this cycle, the raw material is the limestone or the calcium carbonate. And the idea is to decompose this limestone into calcium oxide and CO2 using the solar energy. But also we want to capture the CO2 from this chemical reaction. So it is needed to have a closed reactor. And one advantage of this cycle is that with the solid product, with the calcium oxide, we can use this material to absorb CO2 from, for example, one industrial flue gas, and also this is an exothermal reaction, so we can use the energy from this reaction. But as I mentioned before, one challenge for the rotary kiln to be used in this cycle is to operate in closed mode. And for that reason, we put a window on the reactor front where the solar radiation enters. But here we are talking about different material conditions because the particle size here are in the range of microns. And we observed in one experimental campaign that the finest particles tends to migrate to the window. And after some minutes, the window is covered by particles so that the solar radiation cannot enter anymore inside the reactor, and the window is overheated and it breaks. So this is very well known as the window problem in solar reactors, and this problem has been already studied by several authors, and the most well-known solution until now is the implementation of a kind of system where they inject gas flows in order to create kind of a protection shield to protect the window. But the system or the problem has not been totally solved until now, especially for rotating reactors where gases and solids are involved. So in our investigation, we are trying to look for a system to avoid this window problem, and considering the different requirements for a solar reactor, we found that the electrostatic separation of particles has a very big potential to solve this problem. And in order to describe how it works, I have this diagram. So you can imagine this black point as a wire, which is placed in the middle of this circle, which represents a tube. And if we applied high voltage to the wire, and if the tube is connected to the ground, we can create an electric field between the two elements. And this electric field is characterized by two regions. In the region here close to the electrode, the energy is very high, so we can remove electrons from the gases here, from the gas molecules. But once the electrons passes to the low energy region, the electrons will be attached to the gas molecules, and then these gas molecules will collide with the solid particles, transferring its charges, and the charged particles will move to this grounded surface. So the idea is to investigate this system at high temperature. And for that, we designed this experimental setup where mainly we have this tube, which is divided into 3 parts. And here in this first part, we have the inlet for the hot gases the solid particles as well as the inlet for the high voltage, which is provided by this high voltage power supply, is transmitted here to this through this rod, and this rod is connected to the electrode here. All these parts are electrically insulated in order to control here the discharging region in our high temperature ESP. The gases lives here in the front from the top side of the tube, and here in the front part we have a window to observe what is happening here inside and also to evaluate the performance of this system. The two parameters here to characterize these systems are the current, which is circulating here through this collecting surface, and also the voltage, which is applied here to the discharging electrode. So until now, we tested already the experimental setup at room temperature. So here we can see the inner part of this tube. This white material is the electrical insulation for high temperature, and this uncovered metal surface is the collecting surface. This is the electrode, and we measured the voltage and the current, and for this geometry, which is very similar to the geometry where we are planning to install this system to protect the window in the reactor, the charging process starts about at 24 kilovolts, and if we increase the voltage, the current will increase also, and so we'll do the removal efficiency of the system. But we can increase this voltage up to this value where we reach this spark voltage, because at this value one spark discharge will occur, and we don't want to do that. And also for these systems, it's very well known that this operational gap between spark voltage and onset voltage will decrease at high temperature. So with that investigation, we want to answer what is possible at high temperatures where solar thermochemical processes occurs. And for the next step in my investigation, I'm planning to, of course, to study several particles that are used in solar thermochemical processes, as well as different gases. And the final idea of this investigation is to implement the system to protect the reactor window in the solar rotary kiln. So the first idea is to use this, the entrance region of the solar radiation in the reactor, which is this semi-conical geometry. And in that region, we are planning to install this ESP system. Here we can see, for example, one diagram of it. This will be the electrode here in the middle of this semi-conical structure. And the idea is to separate the solid particles here before they reach the window. And of course, we have to clean this collecting surface. So this is part of our investigation in the Institute. And if you are interested in it, you can feel free of contact me. So thank you very much. And here I put also these references about the projects that I mentioned during my presentation.
Okay, thank you very much for your presentation. And there is some question I see. Okay, there is one from Alfonso Juan Jarillo del Teso. If you want to express your question by yourself.
Yes, for sure. Thank you.
Okay.
Thanks for the talk, Juan Pablo. I was interested about the manganese iron composition you use for your test, and also what is the cause of the deactivation of these materials at 1100 degrees Celsius?
Okay. Yeah, I was involved more in the experiments with the reactor, but yeah, this iron manganese composition was 70% manganese and 30% iron. And yeah, I will refer to the paper about the material part of this project, just to see this the composition of the material. But as or one result of our project was that we could demonstrate the feasibility of this process using big reactors. For the oxidation, we developed a moving bed reactor, and we are looking for better materials, because here we had only this operational gap between this 1050 and 1100 degrees, and so the process can work, but we need a better material.
Cool.
Okay.
I have one question, if possible.
Yes.
So are you willing to study other kind of materials, like, for example, perovskites, oxides? Like, can I propose my material?
Yes, of course. In our institute, there are some colleagues. They are working specific on the development of the materials, and they are also investigating perovskites. And of course, we are open to use new materials. And if they had the perfect energy density and the correct cyclability to run this kind of cycle, they are welcome.
Okay, thank you, and thank you for the talk.
Yeah. You're welcome.
Well, if there are no questions, so thank you very much, Juan Pablo. Thank you for your talk. So we can move to the other section of this webinar that deals mainly with thermochemical fuels production. So it's my pleasure to introduce the keynote speaker for this second part, Professor Sosina Haile. Professor Haile? I think she is here. At least I see.
Okay, is this better now?
Okay, perfect.
Okay, great.
Okay,
Hello.
so thank you to be here. So a brief introduction of Professor Sosina Haile. So she is the Walter Murphy Professor of Material Science and Engineering at Northwestern University, a position she has got in 2015 after serving for 18 years on the faculty of the California Institute of Technology. She earned her PhD in Material Science and Engineering from the Massachusetts Institute of Technology in 1992. So the Haile's research broadly encompasses solid-state ionics materials and devices, and the research particularly focuses on energy technologies. So she has established a new class of fuel cells based on solid acid electrolytes and demonstrated record power density for solid oxide fuel cell. So her more recent work on water dissociation for solar fuel cell generation by thermochemical processes has created new avenues for harnessing sunlight to meet rising energy demands. So she has published more than 190 articles and holds more than 15 patents on this and also other topics. Okay, the citation are more than 12,000 and H index equals 52. Amongst her many awards, in 2008, Haile received an American Competitiveness Innovation Fellowship from the National Science Foundation in recognition of her timely and transformative research in the energy field and her dedication to inclusive mentoring, education, and outreach across many levels. So in her talk, Professor Haile will speak about the influence of thermodynamics on the kinetics of hydrogen production in thermochemical cycling. And she will discuss the connection between the thermodynamics of the reduction-oxidation reaction and the microscopic rate at which the fuel is produced. So, Professor Halley, please.
Okay, since I'm new to this, I'm going to have to find where the share screen is. Okay, I believe you can see it, correct?
Yes, okay.
Great. Okay, it's my pleasure to be speaking with you, and thank you for the kind invitation to participate in this important forum. I will indeed be speaking about the connection between thermodynamics of a material and the macroscopic rate of fuel production. So this is going to be much more materials oriented than you've heard so far, at least from the last two presentations. And I think the talk by Mr. Rincon Duarte is very connected to what I'm going to tell you here in terms of how you can use these types of materials in the kinds of reactors that he described. So the idea is very similar in the sense that we have a metal oxide. We're going to take it to high temperature, allow it to get reduced, and then in this case, expose it to steam or carbon dioxide with the aim of extracting the hydrogen or the carbon monoxide for future use. What we are using here, in contrast to the phase change materials that were just described, are materials that release oxygen and incorporate oxygen without a change in crystal structure. And that is beneficial because that means that we have very high bulk diffusion through this material, and typically also that's associated with fast surface reaction rates. But that means that we want a material that's going to undergo a large non-stoichiometric change with this change in atmosphere. Turns out that ceria is an excellent benchmark material for this. So I'll be describing to you how we understand ceria, but also some of the lessons learned will be applied to other materials. And it's an ideal material because the thermodynamics have been very well studied. So we know exactly how the oxygen content in the material changes as a function of oxygen partial pressure and as a function of temperature. So this is, data back from 1975, very clean data. And how do we use this is the following. We do a sweep of the material at high temperature. So we have an inert gas that has a low oxygen content in it. We heat it up to 1500 C. That induces a loss in oxygen by this amount here. We then quench it to 800 degrees Celsius, introduce steam at that temperature. Say 20% steam would give you an effective oxygen partial pressure of around 10 to the -7 atmosphere by the thermolysis reaction. And then the material in response to this oxidation condition returns back to the condition of delta being equal to 0, where delta is this non-stoichiometry. So we calculate that out, and that turns out to be 8.6 milliliters of hydrogen per gram of oxide per complete cycle. Okay. And so we've done lots of experimental demonstrations of this. Others have as well. So here's the oxygen release when we heat the material up under this inert atmosphere. We get exactly the amount of oxygen we expected. And then after we cool it down and introduce steam, we get exactly the amount of hydrogen we expected. And we've cycled this, hundreds of times, and it's very stable. And you can see that we use a porous ceria monolith here with relatively short diffusion lengths of a few microns and a relatively open porosity. We can't go to nanoscale features because that would, of course, coarsen away at high temperature. One thing to notice here is that this oxygen release is indeed slower than the hydrogen production. And to some extent, you might think, well, if this is kinetic, some sort of bulk diffusion or surface reaction rate limited, you expect things at high temperature to go faster than things at low temperature. This is at 1500 and this is at 800. So let's see if we can understand this relatively slow oxygen release. So this is just zooming into that. And we did the release for this 30 minutes, and this is where we switched over to lowering the temperature. So it takes this full 30 minutes and it continues going on. So let's do a thought experiment. Let's imagine that the material is in quasi-equilibrium, meaning the kinetic steps are infinitely fast. So there is no delay due to surface reaction. There's no delay due to diffusion. That means that the oxide would immediately equilibrate with the gas as soon as it's supplied. And any further changes in oxidation would require an additional supply of the sweet gas. So we want to see, can this explain the slow rate of oxygen evolution? So here's our thought experiment where we have this fixed composition inlet gas. And what we're doing is imagining that the outlet gas composition is set by equilibrium with the solid. So we have a first round assumption to be able to model this, which is that there's a uniform oxygen content across the entire material here. So everything is in equilibrium here. The new piece comes in and changes everything till we get to the next state of equilibrium. So that means we need to understand the equilibration behavior of the solid. And you may have heard this from Dr. Emanuele's talk, but let me add in here just how this looks. So let's say we have Syria undergoing reduction. So now we're going to look at this in infinitesimal change, and we have a delta G for that reaction. And we can write that out as being a delta G, which is at a given value of non-stoichiometry. So we're going to allow this alpha to go to 0. So we're imagining what an infinitesimal change in oxygen content would be, what that equilibrium would be for that reaction. So here's our delta H and delta S. So we can write that out as just being RT ln PO2 to the 1/2, because that's what we get from here. And these two sides are equal, so they don't enter into the equilibrium constant here. Okay, so we're going to evaluate this at a given delta, and this hat here means that this is relative to the reference pressure, which is 1 atmosphere. Okay, so let's evaluate it at a given value of delta naught. All we're doing is saying, okay, let's rewrite this expression here, putting these two together, evaluate it at this given value of non-stoichiometry. We're going to put this together on an Arrhenius plot. So we're looking at all the pairs here of data points. We plot a line from that, and then we get the, from the intercept, we're going to get the entropy, and from the slope, we're going to get the enthalpy of this reaction. So we're going to do this now at all sorts of different values of non-stoichiometry, and out of that, we extract the enthalpy of reduction and the entropy of reduction as functions of oxygen non-stoichiometry. So this is the thermodynamic data we need in order to be able to evaluate the macroscopic rate of gas evolution if we are operating in this condition where the rate is determined by the thermodynamic behavior as opposed to the kinetic behavior. And there's some interesting, materials defect chemistry here. But again, I think for this audience, we'll just note that what we need are these functions. Okay, so now let's imagine how this thermokinetic control can occur. So let's do our thought experiment with isothermal cycling, where we're keeping the material at 1500 degrees Celsius. We're imagining thermolysis at this high temperature with 20% steam, which gives us a moderate oxygen partial pressure of 10 to the minus 3.6. And we're doing reduction with our inert sweep gas, which has, again, this 10 ppm oxygen in it. Okay. So let's zoom in on this plot or this curve for 1500 degrees Celsius. And what we're saying is here's the oxidation condition, here's the reduction condition. So we're going back and forth between these two states, and we want to see what the macroscopic rate control is as we go between those two. So this is our initial, and this is our final. Okay, so how do we get from here to here? Let's look at our material, and before we go into the mathematical model, just look at what it means in a physical sense. That means that we did the oxidation here with this steam, so the chemical potential in and out are the same once we are completed with the oxidation step. So now as we initiate the reduction step, we have this low oxygen chemical potential gas coming in, and our before any gas goes through, we're still at this state for the exhaust and for the material. Now, if we look at what happens with time, the incoming gas has the same chemical potential throughout, and the outgoing gas is slowly moving down in its chemical potential. And again, our assumptions are that the chemical potential is constant across this porous material, that it's in equilibrium with the gas, so this has nice access to the gas. That's why we use that open porosity material. And we want to track how the chemical potential, therefore the oxygen partial pressure emerging from here, changes with time. We know the gas flow rate and we know the mass. So these are the things that dictate the overall behavior: this thermodynamics, the gas flow rate, and the mass of the material. Okay, so now we're going to have just a little bit of equations here. So If we go from that initial to final, this is the actual increment of change, not the infinitesimal, but the true increment that we're changing between those two states that I showed you at 1500 degrees Celsius. Okay. Now, this is our model again. What we're saying is that we are controlling the flow rate of the gas coming in. We have a total flow rate of that reducing gas, and we know exactly what the oxygen content is in that reducing gas. What comes out is a total flow rate of gas, and its amount changes with time, and some fraction of it is the oxygen coming out, which is also changing with time. So these are the things that we'd like to know. Well, the macroscopic rate of oxygen generation should just be the difference between what was coming in and what's coming out in terms of oxygen. So that's straightforward. But now we have a way to write it out and connect that to the change in oxygen content. So if we have some number of moles of material, then the amount of oxygen that's being generated is simply the change in the non-stoichiometry with time. So this is a straight mass balance. And then by definition, this is just the oxygen in is just the partial pressure times the total flow rate going in, so that P is partial pressure, and the coming out is the same thing. It's the amount of flow rate coming out multiplied by the partial pressure of the oxygen in that gas that's coming out. This is the quantity that we'd like to know. We don't know what it is, but if it is in equilibrium with the gas, then we know its relationship to the oxygen partial pressure through our thermodynamic measurements of the material. We have another mass balance step, which says that the total flow rate coming out is just the flow rate that was in plus the oxygen content that we generated through this reduction reaction. So these two are actually independent, and we put it all together, and we have this very simple expression for the change in non-stoichiometry, which depends on the flow rate of gas coming in divided by the number of moles of material that we put into our reactor, and then this thermodynamic term. And this oxygen partial pressure is a function of non-stoichiometry. That is our thermodynamic measurement. So everything is predictable here. We have very, very simple set of assumptions. We need to make sure that our assumptions would be valid if for our actual experiment. But if they are valid, then this is a very simple way to calculate the oxygen release. And we can do something analogous for oxidation, accounting for thermolysis. I may or may not go through that, depending how quickly I'm speaking. Okay, so here are the things we need to know. We have 4 process parameters. I told you the flow rate of gas coming in, the moles of oxide that we put into our material, the oxygen partial pressure in this inlet gas, and the third process parameter is the temperature here. And then this is the parameter that varies with time. So how are we going to use this? So we're going to use our known variation of non-stoichiometry with oxygen partial pressure in a time step calculation. Very straightforward. This is what we evaluated previously in understanding our material. If our total pressure is 1 atmosphere, then partial pressure and pressure relative to the reference state are the same thing. So that makes the calculation straightforward. So here we are. We're going to calculate the non-stoichiometry as a function of time. We have some input starting value of non-stoichiometry. That would be our equilibration, for example, with the steam that did the oxidation of the material. And this term here simply is the slope of the non-stoichiometry with time. So we calculate the slope, we input a time step. So here's our time step, and we use that to calculate the new value of the non-stoichiometry for a given increment. So we can set this as big or small as we want in our calculation so that we can calculate this profile. And then it's done. I think I'm going to skip the oxidation behavior. It's just a little bit slightly more complicated because we have to account for thermolysis, but I'm going to, in the interest of time, just skip all of that, just tell you that there is also an expression here, which is very similar to what I showed you for reduction, but we assume that the gas is in equilibration with respect to thermolysis on the output, and we can then replace this, what we call here the extent of reaction, with the thermolysis equilibrium constant. Okay. Key thing is that the flow rates and the mole of oxygen or oxide that we put into our reactor really matter in terms of the rate of the hydrogen production or rate of oxygen release. So here are some comparisons to the experiment. So you can see that that we do predict our experimental results quite well. So this is the model experiment. We have, of course, some small time delay before we actually reach to the mass spec that is detecting the gas that's evolved. Here it is on reduction. Here it is on oxidation. Similarly, the inconsistency is just in the beginning part where there's gas mixing effects and so on. But the key is to show you that this very long release time is now captured, and it's well explained by understanding the thermodynamics of this material. This tells us Syria is really very hard to reduce. That's essentially the short of it, and so therefore it takes a long time. We need a lot of sweet gas in order to get us to the reduction, equilibrium reduction state. Okay, so other aspects of validating this model, I told you that the oxygen release or the hydrogen production should be dependent on the gas flow rate. And here we change the gas flow rate, and you can see the apparent kinetics then change. And we've done this also by simply changing the amount of material. And this is normalized to the grams of oxide in the material. So it's not simply that we're having a proportional change in the amount of hydrogen, but it is even after we normalize for the grams of oxide that there is a difference here because of that thermodynamic driving force is influenced by how much material we have in the reactor. So we see all of that. We can simulate also the heating profiles. That means just updating the temperature each time in our calculation. And when we heat very quickly, the reactor, in fact, is a little bit behind, or the thermal diffusion through the material is a little bit behind. So we're not quite as high as our thermokinetic model, but at a moderate heating rate of 50 C per minute, we're match well. So all of this tells us that this model is valid. So is there ever a role for material kinetics? And the answer, of course, is yes. If we are doing this oxidation at a lower temperature, so here's how we're changing the oxidation temperature. At high temperature, this is thermodynamically driven. So the driving force gets smaller and smaller as we go to high temperature. So the hydrogen release gets smaller and smaller. And as we go to lower and lower temperatures, eventually some sort of kinetic factor takes over, because thermodynamics would dictate that this should just continue going up and then plateau at around 700 or so. But we see that it decreases, and that's because there's a kinetic limitation. And that kinetic limitation we know is due to a surface reaction step, because if we put a catalyst material on top of our Syria particles, our monolith, we can increase the rate significantly. So where it was starting to be declining without a catalyst because of the surface reaction step, when we have that catalyst material on here, we recover a very high rate of hydrogen production. So what does it mean in terms of changing the material? So I told you that the hydrogen or the oxygen release is very difficult in Syria because its enthalpy is very large. The enthalpy of reduction is very large. So if we decrease that enthalpy of reduction, we'd expect a material to be easier to reduce. But you might think that it's also more difficult to oxidize. So we looked at lanthanum strontium manganese oxide, and this is a material for which the enthalpy does not change terribly much with composition, but the enthalpy does change quite significantly. So Syria was around 400 to 500 kilojoules per mole oxygen, and that's sort of curved slope that I showed you. Here we're about half that, or a little over half that amount. And so let's look at what it does for the hydrogen production step. And what we can see is that the hydrogen production is relatively fast when we have just the 10% strontium, and the enthalpy was still reasonably high. And as we go to more and more strontium concentration, we can see that the rate declines quite dramatically. And now it's taking a very, very long time. And the simulation and the data here are in relatively good agreement again, telling us that, in fact, this is basically what we expect for a material that has a much lower enthalpy of reduction. On the other hand, the productivity, so if we were able to go to an equilibrium cycle, go all the way from one equilibrium state to the next, as we have more and more strontium, we would expect more and more hydrogen to be produced, because this is a larger and larger change in non-stoichiometry. But that peak rate of production is declining. And if we compare that for Syria under the exact same conditions, where we do a reduction of 1400 degrees Celsius and water splitting step of 800 degrees Celsius, these points are almost reversed. This is not a mistake in this plot. The total amount of productivity is quite small for Syria under these conditions. It really doesn't get reduced very much, even under equilibrium. But the rate at which that hydrogen would be produced, because we'd be going to 800 C, where the driving force for oxidation is very high for Syria, that initial peak rate would be extremely high. So this is the trade-off that we need to understand. And this apparently slow kinetics that has been attributed to perovskites having some feature about them that is kinetically slow really is about a small thermodynamic driving force. So with that, let me conclude and summarize and say, look, solar-driven thermochemical cycling is generally performed at high temperature. And as a consequence, the surface reaction rate and the bulk diffusivity in these non-stoichiometric oxides can be very high relative to the rate of gas supply. It isn't always the case, because you can have a microstructure that doesn't have very high surface area, or you could create very long diffusion lengths, or you might be flowing your gas at a slow rate, so you could be outside of this range of thermodynamic control. But in general, thermodynamic control is encountered quite frequently. So that means that the fuel production rate is limited by the material thermodynamics. So we need better thermodynamics, or at least to select the thermodynamics that gives us good hydrogen production at the low temperature and good oxygen release at the high temperature. So somewhere between Syria and these perovskites, we need to tune that enthalpy to where it needs to be. Also, an important thing is that these conventional metrics that we use, like milliliters of hydrogen per gram of oxide per cycle, is not very meaningful, because, of course, we can do a very long cycle and get more fuel. If we do this looking at it per unit time, taking into account the cycle length, that's better, but then that becomes sensitive to the flow rate relative to the oxide mass. So we don't typically report these numbers, but I can show you that we can sort of manipulate this parameter at will simply by changing the flow rate of gas and the material, the amount of the moles of oxide that we put into our reactor. So we need to be very careful about that. So my personal view is that we pay greater experimental attention to the thermodynamic measurements or other ways, so thermogravimetric measurements and other ways of getting those thermodynamic properties. Let me close by thanking my students and postdoc. Most of these folks here have already moved on. Currently, Xin Qian is the student who's worked on some of these perovskites that I've described to you. Tim Davenport was really essential in creating this model that I described to you, and other contributors, William Chue, Mike Ignatowicz, and Chikai Yang, who've done measurements, and William is now associate professor at Stanford, so all people have gone on to great things. Some of this work was in collaboration with Jennifer Roop at MIT, Chris Wolverton here at Northwestern, funding from various organizations. And here's a picture of my group that I like to show with Chicago in the background, but it is it is quite outdated, because we know that our group meetings are now all by Zoom. So with that, thank you for your attention, and I'm going to leave the summary and conclusions up.
Thank you very much, Professor Heile, for this interesting talk. I see there are some questions from, no? Maybe in the chat. I will.
Yeah, it's from me. It's like I don't have my name on the. Yeah,
okay.
I'm Alicia. I want to thank Professor Heile to give this really nice presentation. I wanted to ask you if studying different types of materials Did you see a correlation between delta H and delta S? And if there is any way we could modify the delta S, maintaining the delta H in order to favor the thermodynamics?
Right, so having a large delta S is recognized to be valuable for a temperature swing, and that is much harder to control. And yes, so I think, yeah, you know, if I had some great idea, I would go out and patent it. So I think the key factor is that we really haven't measured it very well to really be able to understand it. And we also know that computationally, that's much harder to predict than the enthalpy. So I mentioned Chris Wolverton as a collaborator here. He's a computationalist, and that is sort of where we're working on it, because he does high throughput calculations. You can do lots of high throughput for the enthalpy. Getting at the entropy is hard. So you think about some unusual forms of entropy. So Syria, the argument has been that there's some electronic entropy contribution that gives it a high entropy. Are there magnetic sources, things that don't necessarily give you a structure change, because again, from my perspective, that causes the material to fall apart, makes it hard to cycle. I mean, I don't know of any other examples of 500 cycles of a given material. So magnetic entropy may be the way to find something, but I don't have an example.
Thank you.
Okay, thank you, Professor Hale again, for the very, very interesting presentation. But we are quite late, so I hope that we have again occasion to have you as a speaker. Thank you very much.
Thank you.
So I will. Okay, now it's time for Dr. Mario Sanchez from IMDEA Energy Institute. Dr. Mario Sanchez will give us a presentation on effects of temperature gradients on continuous hydrogen production. He is a predoctoral researcher at IMDEA Energy in the high temperature process units, and he is sponsored by the Spanish government. So, Dr. Mario Sanchez, please.
Thank you. Thank you for your introduction. First of all, I'm glad that you call me doctor, but I'm not a doctor yet. I'm just a predoctoral researcher. So, well, let's start. Well, thank you for your introduction, and I'm here today as part of the High Temperature Processes Unit from IMDEA Energy to talk you a little bit about our work in hydrogen production. Let's start from something like that Susanne has just explained, that is how these cycles work. Basically, we have a metal oxide, and we heat it up to generate those vacancies, releasing oxygen in the process, and that's just with the target of going back to the first state, in our case, adding water to produce hydrogen. The main driving force in taking into account in these kind of processes are the temperature. Well, the reduction is conducted at high temperature as the hydrolysis because of thermodynamical issues. And well, in our case, we're also working with Syria. So we're basically, when cycling, we're reducing the material at 1500 degrees C, and doing the hydrolysis at around 1000 degrees C, a little bit lower. But the main target of this talk is just to explore a different way of doing this. Instead of doing a two-step cycles, we're trying to do it in a single step. So basically, we're just working at the same temperature and just check if we're able to injecting water, if we're able to split it directly into hydrogen and oxygen. To do so, we have a vertical tubular reactor that Emanuela presented you before that we use also for her study with the perovskites. And well, here you got more or less the flow diagram that we use for this experiment, in which we pump argon in the system. So just to remove the oxygen for the process, and we also inject liquid water just because this liquid water will evaporate all along the tube, hopefully before reaching our reacting bed. Then this flue gas is just condensed, and we remove the water and get to an analysis graph that for this experiment basically consists on a micro GC. As you may imagine, our bed, we're placing our bed at the bottom of the reactor, so we take advantage. So just to try that most of the water is evaporated by the time it reaches our reacting bed. This bed is composed of Ceria particles that are more or less 2 millimeters diameter and 3 millimeter long. And those particles were developed by the Institute of Catalysis and Petrochemicals from Petrochemistry from CSIC. And you can see here the difference of these particles when we first introduce them into the reactor, and those that we take out after about 50 hours of use. We're talking about hours and not cycles, basically because we are trying not to cycle but to do the process in a single step. If we just check the characterization of those particles, the main difference is between the most noticeable difference in the used particles is that there are some that are blue, and as far as we know, this is due to the presence of hydrogen during the reduction stage. So it's something again that we can expect since we are working in a single step. So that's why we divided here between these two types of particles. And here in the bulk density pink particles that are those that are more or less the same as they get into the reactor at first, presents a relatively smaller bulk density, but the main difference is here in the breaking point. We use a dynamometer to measure it, where the blue pellets seems just much more fragile than both the new and the pink ones. Well, nevertheless, you can see those differences in the particles. We saw no negative impact on the reduction rates. Well, and how are we testing? Basically, what we did was we chose 3 key parameters that are temperature, the water concentration that we inject, and the total mass flow rate. And we just switch one by one, maintaining the other 2 constant for several tests. And it is a way, all tests were run more or less under the same conditions, in which we just get around 8 grams of Ceria particles inside the reactor. And as I said before, they're just located at the bottom part, just to trying to get most of the oxygen or most of the water evaporated by the time it reaches the reactor. Well, this is the plot of the first test, of the temperature test we run. This is raw data basically, and what we did was just increase the temperatures just step by step on our requirement, and just stay there for 2 hours. We keep the water injection during all the test once we reach our first set point, and afterwards just to treat those data. What we did was just do the integration and normalize the results depending on the real time and the actual Ceria mass inside of our bed. So now well, obviously for oxygen and hydrogen. So now we can start moving on the results. Here, what we see for the first test for hydrogen is for hydrogen production in the temperature test, is that when we increase the temperature, we also increase the hydrogen production. That is something that we thought is normal because of the reduction extent of the material, the vacancy concentration. The higher the temperature is, more for the same concentration of both water and oxygen, then obviously there will be more vacancies available for the water to attack and produce the hydrogen. In case of the water concentration, we see something similar. It's just taking a look at the equations that I saw before, the thermodynamic and the kinetic one. It just says that if we have more partial pressure of water, we're able to. The kinetics will be a little bit faster. What really surprised us a little bit was the behavior of the inlet flow rate on the on the hydrogen production. That obviously may be also because of the diffusion issues inside of the, along the bed and even inside the particles. But also, I think, we think that can be an issue if we consider that this is our reacting bed, and we're injecting liquid water from the top, and we assume that not all of them are going to evaporate. It would create a cold area here that obviously will be increasing while the temperature, while the flow rate increase. And we think that materials may affect this big gap that production increases more or less 6 times in the data we used. And this may be a cause that we have not really doing an isothermal test, but for this liquid water injection, we're creating 2 areas in the reactor. One of them at low temperature and another one at high temperature, in which the reduction takes place, and then somehow it promotes the vacancies to the let's say the hydrolysis part in which we produce the hydrogen. If we check at the oxygen production rates for the temperature and the flow rate tests, they are more or less the same as the tendencies are more or less the same as those for hydrogen. It's not the case for oxygen, where the concentration becomes more or less constant for no matter the concentration of water we include. But I think that's something that we can better understand by checking the hydrogen-oxygen ratio. If we're assuming that we are at thermodynamic equilibrium, then this ratio should be 2. If we're able to split water, the concentration of hydrogen should be always double of the oxygen one. What we think is again, is what Sosine just explained, that even if we are close to the thermodynamic equilibrium, we are not at that point. And that is what enables us to continuously produce hydrogen no matter the case. Here in this case, we're just producing more hydrogen than expected. So basically, we are covering some extra vacancies that were reached before. While in this plot here, when we consider water concentration, is the other way around. We are generating more vacancies than those that we are covering that we are using to produce hydrogen. And something quite peculiar happens with the flow, in which we go through this line from a place in which we generate those vacancies to another place in which we consume them. So, well, just to conclude and just give a brief overview of this work, well, we were able to continuously produce hydrogen, and this production is enhanced by the increment of all the 3 variables that we studied. Additionally, we can consider that hydrogen is produced in a stationary regime. Let's say that, concentration in almost every step at 1300 degrees C, there was this peak and also this value. But you can see that there are plateaus at every temperature, and this happens for all tests. But if we check the hydrogen-oxygen ratio, we see that this is not the expected for a thermodynamic equilibrium. So that's what we think, is that we are in somewhere close to the equilibrium, but in which oxygen and hydrogen can still be produced in a different proportion. And then considering the inlet flow rate affects the production rate, that is something that if we don't only consider consider only the diffusional issues, then it's something that can be explained. But we also are taking into account quite seriously the effect of this temperature gradient in the axial coordinate that may be causing also the effect of getting this continuous hydrogen production. And basically right now all these theories are just amazing, but we need to demonstrate them, and we're working on developing a model that is able to explain the behavior of the system. I'd like to acknowledge the 2 projects that allow me to do this work, and also the Institute of Catalysis and Petrochemical of CSIC for providing us the pellets that we use for these tests. Thank you so much. Now I'm open to any questions you have.
Thank you, Mr. Okay, yeah, there are many questions. There are many questions from Professor Halley. Maybe Professor Halley, instead of reading it, you can. Okay.
Okay, great. So nice work. I like your reactor design. Just a few things. One is I really do encourage you to try to implement this calculation scheme. It's really very simple to see if that's what's causing this change in productivity with flow rate. Very straightforward to do this calculation. A few other things are, it might be interesting to do Raman spectroscopy if you haven't done it yet, to look at those different pellets and see if there's something you can learn about differences in the defect chemistry. Oxygen vacancies show up very easily by Raman. Hydrogen incorporation is a little less likely, but you can't rule it out. And it would be interesting also to keep track where those pellets are when you take them out. So if there's a region in the reactor.
Yeah, I mean, it would be great just to know where they are. The problem is that when you remove the cube, basically all pellets along with the bed that is holding it just fall into the steel piece down.
Okay, but maybe you can mark them in some way, like put a cut or a mark or some sort of physical obviously not a color, but a shape difference, like make some of them taller in some region, or it's something like that could allow you to track where they are.
Yeah, maybe a good idea. Thank you.
Yeah. The other is, one thing to be careful of when you're doing this very high temperature isothermal cycling is to make sure that you don't quench the thermolysis. So because you're going to get some thermolysis that happens, and if your gases cool down very quickly, you may not recombine the oxygen and the hydrogen from the thermolysis. So you would end up overestimating the hydrogen that's produced from the oxide itself.
So I don't know if I fully understood that. I mean, the thing is that obviously when you are at that temperature, when you're producing both of this material, they are going to tend to recombine. So
right. So what happens sometimes when you have thermolysis that happens at high temperature, right? Some of the oxygen oxidizes the ceria, right? And then you have a difference between hydrogen and oxygen at high temperature, and that difference will still include some residual thermolysis. Just the equilibration at high temperature of that gas is going to be different than at a lower temperature. So you want to be sure that you're not overestimating the amount of hydrogen that's produced by the oxide. So we generally put a catalyst in. Of course, if you want to maximize the hydrogen production, you don't put an extra catalyst in. But if you want to know how much hydrogen is produced by your oxide, you put a catalyst in the exhaust. That's just like a platinum or rhodium or something to recombine the hydrogen and oxygen that's in excess. The part that's from the thermolysis. So you only get the excess of thermolysis, which is your oxide producing it. But maybe this is too much detail. So.
Okay.
So I will keep it in mind, of course. Thank you.
Okay. All right.
Thank you to Mario Sanchez. So now I think it's time to go further, and it's time for Dr. Alfonso Carrillo.
Hi.
Okay. So, Dr. Alfonso Carrillo received his PhD in chemical engineering from Universidad Rey Juan Carlos in Spain, and his PhD was conducted at IMDEA Energy in Spain. And then he moved to Electrochemical Materials Laboratory led by Professor Rupp to perform his postdoctoral research on redox material in different labs at ETH in Zurich, and after at the Massachusetts Institute of Technology in the USA. So the talk, it's on functionalization of redox oxides with exsolved nanoparticles for the production of solar fuel via chemical looping reforming. And it's very interesting talk about the concept, the new concept of a nanoparticle exsolution as an efficient route for the creation of metal nanoparticles well attached to cilia. So, but Dr. Carrillo will give us all the details, please.
Hi, thanks everybody. Thanks first to the organizers for this kind introduction. So today I'm going to talk about the functionalization of redox oxides using the exsolution method and how this can be applied to the production of solar fuels via the chemical looping reforming of methane technology. This is a brief outline of the talk. First, I will explain why it's interesting to investigate on this chemical looping reforming technology and why the exsolution route is a nice way to prepare stable metallic nanoparticles decorating our oxides. I will start talking about my previous work at MIT with Professor Rupp on this matter, and then I will show the latest results I'm currently doing at the Instituto de Tecnología Química. So as a nice follow-up to the previous talks by Professor Jalí and Mario Sanchez, I'm going to show this two-step thermochemical cycling. However, here the difference is on the reduction reaction. Here I'm going to use methane as a reduction agent, and therefore we will have on the first step what I call the solar-driven methane partial oxidation. We will reduce urea as our redox material, and we will create oxygen vacancies on the material, but we will also produce syngas on this first step of the thermochemical cycling. On the second step, we will inject CO2 and water on the reactor. Our reduced oxide will uptake oxygen from these two molecules, and we will produce also step. So why this process is interesting? First, it allows us lowering the process temperature down to 900 degrees Celsius because we are using methane as a reductive agent. We will also obtain larger reduction extents and these lower temperatures. And syngas is produced in these both steps. And this obviously affects to the solar to fuel efficiency of this process with by calculations of Professor Jane Davidson's group from University of Minnesota is up to 39% for the zero redox couple, which if we compare to traditional thermochemical cycling, experimental solar to fuel efficiency record of 5.25% obtained by Professor Steinfeld's group at ETH. And also, it's a clean alternative to steam reforming, which is the main source for hydrogen production worldwide. It represents 95% of the hydrogen produced. This technology also gives us sustainable avenues for natural gas processing to renewable fuels. And why this is interesting, if we look at the projections of natural gas, we see in this graph on the top that the amount of natural gas is going to be increased on the next 30 years. So probably it's interesting that we can use a renewable source such as solar energy to transform methane into syngas that can be further processed in other chemicals rather than just combust methane and to produce heat and produce CO2 as well. And the main source of this increase in natural gas, I believe, will be coming from shale gas. This amount of shale gas is almost as high as the conventional gas by 2015. mainly countries like USA, Canada, Argentina, China are producing a lot of shale gas. So I think it's interesting if we can transform methane into other chemicals using solar energy or renewable energy sources. But of course, there are some challenges with reactions. And here, the challenge with cerium oxide for the methane passage oxidation is first the kinetics of this reaction. I'm showing here a plot that represents the versus time for this reaction at the top. The production of hydrogen and carbon monoxide is quite flat. It's not a fast process. There is also challenges with side reactions because methane can combust with the oxide, with the oxygen at the surface of the oxide, and produces water and CO2, as observed also in this graph at the very beginning of the reaction. Methane can also crack and form hydrogen and carbon depositions, which affects to the hydrogen to CO ratio. These carbon depositions, if we do CO2 splitting on the next step, will be transformed into carbon monoxide, so we can somehow get rid of it. So we need to tackle these challenges, these limitations, and for that we are gonna make use of material science and engineering because we need to find more stable and efficient redox catalysts for this technology. And I like this graph by Professor Fan-Xin Lee from North Carolina State University, and they suggest these alternatives for improving the properties of a material, such as surface treatment, nanorods, or using composites. But if you dig in literature, there are many others as additional support, like zirconium oxide, shaping into nanostructures like this beautiful flower-like cerium oxide, addition of dopants, we have been done a lot with cerium oxide, and or addition of catalysts, metallic catalysts, these ones that will be the point of my talk. And by all these changes in our materials, we can change textural properties or thermodynamics, and this will improve the catalysis toward higher selectivities or conversions of methane, which is what we are looking for. Since I'm talking about the incorporation of metals into our oxides, traditionally this has been done by impregnation methods or deposition. Here you put your oxide or nitrates or other precursors, you reduce it, you will create your metallic nanoparticles, but after several cycles, your particles are going to sinter with neighboring particles, they are going to grow, and their catalytic activity is going to decrease over time. As an alternative, we suggest to use the extrusion method, which has been studied a lot recently on the SOFC community. We thought it would be interesting to apply this concept here. By extrusion, we will incorporate our material of metal of choice into the lattice of the oxide. And there, afterwards, by a reduction treatment in hydrogen, 100 degrees Celsius, for instance, these cations that are in our crystal will migrate to the surface of the oxide, creating nanoparticles that are well anchored to the perovskite backbone or CEA backbone. And since they are anchored to the oxide, they have inherent stability over time, and they will not sinter with neighboring particles. This is a schematic that I like a lot from Dragos Neagu. I actually recommend to read the literature from Neagu, Kelly Kusi, and Ian McCaffrey's group. And they have explored the kinetics of how these particles grow with in situ TM. This is an amazing paper to read if you are interested on the materials science part of this process. So this is our schematic of what we are studying here. We will use the solar energy to drive the methane passage oxidation. We put our metallic nanoparticles to improve the kinetics and the catalysis of this process. And in the second step, we will inject CO2. It will reoxidize the reduced material, and we will produce carbon monoxide. And this is work that I started at MIT with Professor Roop. And we started with this material because previous work by my good friend Alexander Borg showed that this material can actually split CO2. And also we thought, why not using this material if cobalt can also be exsolved as a metallic cobalt? So this is an SEM of the pristine material, and after reduction in 5% hydrogen, 10 hours and 100 degrees Celsius, we observed the appearance of these tiny nanoparticles of about 30 nanometers that they cover the surface grain boundaries of the perovskite. And we further do TM, EDX on this material to investigate which is the nature of these metallic nanoparticles. And as we expected, the metallic nanoparticles are only composed by cobalt, as you can observe in these beautiful TM images that were taken by my good friend Zachary Hood. So we carry out the reactions with these materials. On the top left, we saw the hydrogen production rate versus time for the XOLV material, the material without nanoparticles, and Syria as a reference. And we observed that the XOLV cobalt nanoparticles increase the kinetics for the MPO respect to the bare perovskite. And also we carry out the stability test and saw that after 28 cycles, hydrogen and CO production is quite stable and the particles are still there, so which is quite good news. And when I was looking about the top left image, I was wondering if we can also do that to Syria. Can we actually apply the exclusion method to Syria to improve the kinetics of the process? And this is what motivated me to start with this new research that I'm carrying currently. So let's move to that. So to answer that question, yes, we can actually XOLV metal nanoparticles from a fluoride structure such as Syria. Here, what we use is ruthenium-doped Syria. We thought that ruthenium could be a really good catalyst for this application. And so if you observe here, if you compare the as per image with the SEM images after the extrusion treatment, you can observe that after 2 hours of extrusion treatment at 900 degrees Celsius, there is the appearance of these tiny nanoparticles that are covering the surface of the cerium oxide. If we increase time, we also increase the size of the particles, and they tend to grow more on the edges of the grains of the cerium oxide. We analyze these materials by the XRD, and we observe that all of them preserve the fluoride structure, obviously with some structural differences that we also check by Raman spectroscopy. As Professor Haile suggested to our previous speaker, this is a very interesting technique to study cerium oxides. We observed that by ruthenium doping, there is a lattice expansion, and this was quite intriguing at the beginning. And we think that the reason is that the ruthenium goes to the interstitials. And after exsolution, since we are doing this treatment in a reductive atmosphere, we observe that there is the creation of oxygen vacancies that can be seen in the Raman spectra at around 550, 600 wave numbers. We also did TM of these materials to further corroborate that there is some anchorage of the ruthenium nanoparticles. And if we do see this high resolution TM image, we can observe a very tiny nanoparticle that is anchored or is embedded in the cerium oxide backbone. We further do XPS to understand if this is actually ruthenium metal. So checking the ruthenium core level, we observe a shift on the spectra of the ruthenium after exsolution that suggests that we are actually creating metallic ruthenium after exsolution. So this was good. So we moved to testing the materials. For production performance was done in a high temperature Weitz reactor. We checked different temperatures. Initial tests were done injecting 5% of methane and then doing CO2 splitting with 5% of CO2. And here I'm showing the gas production profiles for a reduction oxidation cycle with the Syria at 900 degrees Celsius. When we inject methane, there is the production of CO2 and also the steady production of hydrogen or the flat production of hydrogen and CO, as was observed previously in literature. And after we inject CO2 in the reactor, we observe the formation of carbon monoxide. So we also test our material with XOLV ruthenium nanoparticles, and we observe a very interesting and remarkable increase on the production of both syngas and carbon monoxide during the CO2 splitting reaction. We observe other magnitude increase on the hydrogen production rates with the XOLV ruthenium material, 33 milliliters of hydrogen per minute per gram, whereas for Syria it's about 3. We also observed that we can improve the selectivity towards syngas, 98% for this material, whereas for Syria it's just 18%. We also evaluate different temperatures. If we lower the temperature for Syria, the amount of syngas reduces a lot, although still there are declaration of some vacancies that allows CO2 splitting on the oxidation step. Whereas for our material with the soft ruthenium nanoparticles, we observed that even at 700 degrees Celsius, there is a very interesting amount of syngas and CO2 split in the reaction. We check, obviously, the durability of these materials and of the process as well. And here, for this experiment, I increased the amount of CO2 in the CO2 splitting reaction. Increasing the amount of CO2, the CO2 partial pressure will increase also the gas production rate for the CO2 splitting. We observed that this is very stable. And we also check by TM the materials after these 20 cycles at 900 degrees Celsius, and we observed that the ruthenium nanoparticles are still there attached. So going to the conclusions, I think, although here we are obviously using natural gas, fossil gas is maybe an efficient alternative and sustainable alternative to other ways to use methane. And given the projections, this might be interesting. We also demonstrated that we can exhaust ruthenium from cerium oxide with well-dispersed ruthenium nanoparticles. And we also demonstrate that this is quite stable in this 20-cycle test, and also the ruthenium nanoparticles remain well attached to the cerium oxide. I want to end up thanking the group I'm working right now, the Instituto de Tecnología Química, which is the energy conversion and storage group led by Professor José Manuel Serra, and also the funding from La Caixa Foundation. And before I pass to the questions, I want to give some promotion to a special issue we are organizing on Frontiers of Energy Research, co-organized with Alicia Bayón Coronado and Emanuela Mastronardo. And it covers the topics that are being discussing in this fascinating forum. So please, if you are interested, just go to the website, check the research topic description. If you have any questions, just write us an email. We will be delighted to have your contribution. So thanks a lot to all for attending this seminar. I think it's one of the largest audience I ever have lately. Thanks to the organizers for inviting me to give this talk, and I'm open to answer any of your questions.
Okay, thank you. And okay, there will be a lot to speak on, but we don't have very much time. I hope you don't mind. I will ask to Mattias Accoccio only to do a question. One of the two questions he wrote on the chat, please. If you don't speak, I will. The first is okay. Okay. The first question is, with the time, the nanoparticles appear to be bigger and located on the grain boundaries. So how can you exclude that they have not dissolved on the surface and then migrated to the grain boundaries and agglomerated later on?
Well, we checked the anchoring of the nanoparticles by TM, as I saw later. Is the materials with these lighter nanoparticles, we didn't look at them much more after we saw that it was better just to do 2 hours of exsolution. Time-wise was better, and the dispersion of the particles look also better than the other case. Certainly, that's an interesting question that we should look at it, but probably there there is, I mean, in the solution field, it's well known that if you increase temperature of the solution treatment at time, you will have larger particles. So maybe these particles prefer to go to places in which surface energy are lower, such as gray boundaries or edges. But I don't have like an accurate answer to this question since we haven't looked at it yet.
Yeah, okay. Actually, talks are like this, and maybe, as I told before, it would be nice to have much more deeper discussion on the sample, on the materials, but unfortunately we don't have time, so we have to organize another meeting to discuss on this. Okay. So thank you very much. So sorry for the other question, but we go further to Dr. Johannes Gröbel from Institute of Solar Research of the German Aerospace Center. And Dr. Gröbel received his PhD in mechanical engineering at Aachen University in Germany in 2019. Currently, he is a postdoctoral researcher at the Institute of Solar Research DLR in Germany, that we already know. And he is coordinator of the Federal States project Solar Fuel Now and project leader in the regional funded Hydrogen Loop project. He also contributed to other projects like Traxol and STCH. So in his talk, operation optimization of an array of receivers reactor for solar fuel production, he will address the question how to distribute the solar power provided by the heliostat field to an array of receiver reactors to obtain maximum hydrogen yield. So, Dr. Gröbel, please.
Okay, can you see my screen?
Yes.
And hear me? Okay, good. Yeah, thanks for the introduction. I'm not going to repeat the title again here, and I hope the slides will move. Yeah, okay. Yeah, so my motivation is thermochemical hydrogen generation, and I think this cycle is now known to everybody here. So I'm also talking about the thermochemical redox cycle to split water into hydrogen and oxygen. And the first step, concentrated solar power is used to heat up ceria to high temperatures, and oxygen is released. And then in the second step, steam oxidizes the metal oxide again, and hydrogen is released. And this process happens in a reactor shown here. The ceria is arranged in a half dome shape to create a cavity, and usually there's also a window in front of the receiver to separate the atmosphere in the receiver from the one outside. And this window is limited in size because it can just not be produced in a large size. So for a scaled up version of the receiver, we have, for the process, we have multiple ones of these reactors on a solar tower, and they are irradiated by a heliostat field. And now there is the question how to distribute the power from the heliostat field to the reactors to obtain maximum hydrogen yield. And these questions here, so to operate, how to operate each reactor and how to distribute the available power, I would like to answer here in this talk. Therefore, I want to first discuss about a reactor model for this reactor. Then I want to discuss the operation of a standalone reactor, and finally the operation of a reactor array. First, coming to the model, I developed a model inspired by my colleague Alon Lidor, who is now working at ETH. And this model, in this model, the main components of the reactor are represented, namely the window, the porous ceria absorber, an inner housing, which is a metal wall here, another metal wall, which is holding the insulation itself, and I also included the inlet mass flows and the outlet mass flows in the model. The radiation contributions were calculated with spectral view factor models, and for the preheating of the gas flow, I developed a model similar to a heat exchanger model, so for these areas here. The insulation is modeled by a transient one-dimensional heat conduction equation, and the most important part, the absorber, is discretized with a one-dimensional finite volume method, and the solid and fluid phases are described by two partial differential equations which are coupled. And I also included the reduction and oxidation reactions in the energy balance. So with this model, we can have a look at the reactor cycle. Here on the top right, you see the temperature profile along the absorber. And you can also see the reduction extent as a dashed line here on the right-hand axis. And in the bottom right, you see the temperature of the absorber front, the temperature of the absorber back in yellow, and the temperature of the window in blue. And now when you irradiate the absorber, you see that at the front the temperature rises quite quickly, and with the temperature also the reduction extent. But you can also see that there's some temperature gradient along the absorber, and in the back of the absorber, basically, there's no reduction happening. Now, when we switch off the radiation and switch on the steam flow, we can see an interesting phenomena. So we see temperature drops in the front and the reduction extent as well. But we also see that the reduction extent in the back suddenly increases. And this is very interesting phenomena. And in fact, the hydrogen, which is produced here in the front, acts as a reducing agent and reduces parts of the absorber which were not reduced before here in the back. And you only see a peak in this graph here. So a peak of hydrogen at the outlet, as marked as a dashed line, when the reduction extent at the exit or at the back of the absorber is greater than 0. So now there's a question how to choose the reduction durations and the oxidation durations to obtain a high hydrogen yield. And here I plotted these durations and the hydrogen yield in this contour plot. And as you can see, there's quite a range of combinations of reduction time and oxidation time where you get a good hydrogen yield out of the reactor. So this map is for a certain flux during reduction. And now to analyze a multi-reactor operation, we basically made made this investigation for a single reactor for different fluxes. So we chose different fluxes during reduction. And for these fluxes, we determined the best reduction durations and oxidation durations. And as you can see, the reduction duration decreases with the flux. Here, I have to say that at the higher fluxes, the duration is actually limited by the material limit of the Ceria, which is about 2000 Kelvin here. And you can also see that, for lower fluxes, the oxidation time remains quite similar. And here at the higher fluxes, it also decreases. This is because here you don't want to spend too much time in the oxidation phase when you have such short reduction times. Interesting to see is also that you have a high, or that the efficiency peaks at a different point than the hydrogen yield. And this is due to the different ratio of oxidation time and reduction time here. Okay, so now we have different combinations of reduction time and oxidation time for different heat fluxes during reduction. And now for the multi-chamber operation, we are going to use these single chamber strategies and combine them for this multi-chamber operation. So, and this is, I want to show you this here on this slide. So we developed a very simple heuristic, I would say, where we divided the reactors into 2 groups. And in each of the groups, all reactors follow the same strategy, but in each group, the start of the process is offset a little bit, so that reactors can operate or do the reduction while another reactor is doing the oxidation. So, and here you see an example with 10 reactors, and here on the top you see indicated the power which is provided by the heliostat field. So when you just have very little power, here 200 kilowatts, you can just operate 1 reactor with strategy 1. In green indicated is oxidation, and red is the time when you reduce the seria. And now when you have more power available, and available power increases, you can operate strategies 2 and 3, at some point strategy 4, and then you have enough power to operate 2 reactors simultaneously, but just at the same time. You have certain periods here where both reactors are in oxidation, then you don't use your provided power, and that's why the heliostat field utilization, which is indicated here by the blue line, is not 100%. Yeah, when you further increase the power, you can operate more and more reactors. Here you see 2 groups of reactors having a different strategy. So there's some period, or there's some power left over from these 4 reactors here, which you can use to operate the 5th reactor, but with very little power. And then you can further, or when you further increase the power, more and more reactors can be operated. And here it's also interesting to see when you increase the power from 1.6 megawatt to 1.65 megawatts, you can actually, according to this heuristic, the number of operated reactors is reduced from previously 9 with strategy 8 to 8 with 2 different strategies. But these strategies are better than the strategy 8, so this makes more sense for the algorithm here. And yeah, when you further increase the power, at some point all reactors can be operated, and at some point also all reactors are in the same strategy 5. And as we have seen in the previous slide, this strategy is the best strategy for a single reactor. So when you think about it, this is the best you can get, because if every single reactor is already in the best strategy for itself, then the whole system cannot get better. So in this case, the hydrogen production rate of the entire system remains the same, but the utilization of the heliostat field decreases. Yeah, so, and this is it already. So I'm already at the end of my talk. So I showed a fast and robust way to find an operation strategy for multi-chamber reactors. I have to admit, this is just the very first approach and it has to be improved. But so far, I think people did not study this a lot. So it was a first step to do. And we made a lot of assumptions, and in the future we will definitely have a look at them and try to live without them and reduce them. So we will have a more flexible solar flux, also include the mass flows in the optimization and have more flexible cycle times. We will represent the heliostat field with a ray tracing software, so a better representation there. We will integrate the up and downstream processes, and we will compare our rather simple heuristic with more sophisticated optimization approaches. Yeah, thank you a lot for your attention. And if you have questions, please ask.
Thank you. Thank you. Thank you for your talk. And there are some questions. One.
Yes, I have a question. Jonas, thank you so much for your interesting presentation. I would like to know if you considered which could be the impact of using a different material with respect to Syria. So using, for example, another oxide which might have a larger reaction extent.
I did not consider this yet, but I mean, in the end, it's I have this model behind all this optimization, and yeah, then I would say the points or the operation points would change with a different material, but I think or at the moment I'm more interested in the overall optimization of this multi-array arrangement, how to do this optimization. Yeah, I mean the Syria, I think with Syria it has a rather low reduction extent, and then you need a lot of oxidizer stream. Yeah, I mean it's difficult to answer if another material would be better. So far, I would say Syria is kind of state of the art, and it's hard to beat. But yeah, we are
Sure.
at the moment we are going with Syria, and we will also perhaps as an outlook. I have another slide here. In the end. As an outlook, this is a project just started, and we will also demonstrate such a multi-chamber operation, and the reactor will also have Syria. But we have other groups, or in our group there are also people developing materials. So, yeah, there might be a better material at some point. But yeah.
Okay, thank you so much.
Thank you. Thank you again to Jonas Gröbel. And so we go to the last speaker, that is Dr. Alicia Bayon. Alicia Bayon is Assistant Research Scientist at the Arizona State University. She received her PhD in Chemical and Environmental Engineering from the Rey Juan Carlos University and IMDEA Energy in Madrid, in Spain, 2014. She worked at CSIRO Energy in Newcastle, Australia, as a postdoctoral fellow. So in her talk on technico-economic analysis of thermochemical energy storage systems based on solid gas reactions, she will propose a quantitative assessment methodology based on technico-economic performance indicators for the comparative analysis of different thermochemical energy storage and fuels production systems. So please, Alicia.
Thank you for your kind introduction, and thank you for inviting me to participate in this
Alicia,
webinar.
your microphone is switched off.
Okay.
No? Okay.
Can you hear me now?
Perfect. Okay.
Yes. Can you hear me?
Yes.
Okay. I was thanking you very much for inviting me to this webinar, and I'm gonna be maybe a not very scientific presentation this time, and it's gonna based on how I did some work on technoeconomics for either thermochemical energy storage, but I will also present some work that is not being published yet on hydrogen, thermochemical hydrogen production from Syria technoeconomic as well. First of all, I wanted to introduce why technoeconomics are important, and I think they are essential for us in order to compare different technologies and to find possible drawbacks of our proposed processes and materials. We also have to know the feasibility of our project, not just the back of the envelope calculations, and that will also help us to understand how our technologies fits in the real world. However, there is a lot of lack of cost data that is not easily available, so doing technoeconomics is quite hard. We have to also make a lot of assumptions, and sometimes our calculations could be either too optimistic or too pessimistic. We have to implement cost equations, and sometimes we cannot compare that equations to other works. And there is an overall lack, I think, of system simulation tools that can cover very different processes and models. So different system simulation tools or different model assumptions will also give different techno-economics. So there is a really need of development of systematic analysis to help decision making. In this presentation, I'm going to present two different types of techno-economic analysis. The first one, I performed this for thermochemical energy storage systems. This techno-economic is based on the sign point equations, basically a steady state. No transients are considered here. That there is included the design of the different subsystems, like the heat storage tanks, heat exchangers, the gas storage and compressors. And also I gathered as much as possible cost data from materials, also construction materials, labor cost and equipment cost, which was a quite hard task to do. In another type of techno-economics, I used the annual simulations doing a dynamic performance of a Syria plant that I will present later. In this annual performance analysis, we could have a full plant description and also an optimization of the different components. But here the cost data is different from the cost data of the top one, because I used the Ilios field cost, receiver cost, tower cost, reactors, balance of plant. Some of them I had to make assumptions for it, and while in the other one I didn't make assumptions of the cost data. The first techno-economic analysis is very helpful to compare different systems with the same plant configuration, because obviously it doesn't account for the full plant, while the second techno-economic analysis is very good to compare processes within each other. For the thermochemical energy storage work, I consider two different possible configurations, although more plant designs could be possible too. There was these two systems based on how is the solid gas reactions and if we need to store the gas or the liquid, or we don't need to store the gas. For example, for carbonate thermochemical energy storage, also for hydroxide thermochemical energy storage, we will need to store the reactive gas because it's not available in the atmosphere. However, for redox metal oxides and the other and redox chemical looping, we can exhaust the gases and we don't need to have that gas storage. The particles are stored in two tanks. The hot tank is also serves as a reactor for the exothermic step, and the cold tank helps for storing the particles before the heliostat field is operating. The main assumptions of this work were that the densities were lower than the bulk. There was perfect solid heat transfer in the tank, so I didn't account for the transients of the heat that could happen during the endothermic or exothermic reactions. All the cost data came from as much as possible from the same source, and also I only calculate the cost of the storage component, not the cost of the full plant. And that came to this graph of results where we can, first of all, classify different materials depending on the exothermic, the temperature of the exothermic reaction, which is the discharge process, depending on the power cycle that we are going to use. For example, some materials will have a higher exothermic, discharge temperature of the exothermic temperature will be coupled with air Brayton or combined cycle, while the lower temperature ones will be combined with subcritical steam Rankine. I also did the economics of the two salts and compare the techno-economics of the two salts with other works to sort of validate this methodology. We can see here that in the range of subcritical steam Rankine, there is only 3 materials that could have an economic interest or a lower cost than a molten salt. Again, this is only the cost of the storage. It doesn't consider the receiver cost. And that could be attractive for further development. Other carbonates, other systems like, for example, dolomite thermochemical energy storage will have a quite significant high cost, although it could be possible to have a better cost performance with other system configuration. In the subcritical or supercritical CO2, there is one commercial molten salt that is a bit more expensive than the normal sodium potassium nitrates. Still, there will be only maybe a couple of systems that will compete with this molten salt in that range of temperature. And for higher temperatures and other power cycles, there will be no competitive molten salt so far. So the materials that has the lowest cost performance probably have a better will have a better like more interest in investigating them. However, I have to say that normally what happens is that with carbonates and hydroxides, they suffer from slow kinetics, while the redox metal oxides and chemical looping reactions, they have fast kinetics. So this was not accounted in the techno-economics, and probably is also one characteristic to have into consideration. So after doing this work, I recognized that it was a need to do a better techno-economic analysis that can include not only the storage part of the plant, but also the rest of the system itself. And that is possible with system modeling. The benefits of doing some system and dynamic system model is that we can compare the whole plant of the different configurations. We can also account for different efficiency of the subsystems. For example, the power cycle efficiency. We account for annual production, not only the design point equations, and also annual efficiencies. And also we can optimize, thanks to system modeling, we can optimize every system depending on the location, depending on the temperature that we want to operate the receiver. We will account also for off-design performance and how that could affect the techno-economics. This is quite important. And we can use calculations based on internal rate under tour and net present value, because we will have basically the full investment of the plant. So that will help much better in the decision making rather than just the cost of the storage. Again, the main drawback of doing this techno-economic analysis is that we have to do some assumptions. For example, there are no, or I'm not aware of any receiver or a commercial receiver that we can use cost from. So we performed this work. We did several plant configurations, not only the one that is shown here. We published few articles of this system modeling of the Syria thermochemical plant. In this case, we designed, I have to say that we designed two different configurations. This configuration is a system where particles are flowing through the plant. Therefore, we can decouple the receiver from the hydrogen production reactor, and that helps us to modulate the control of the system in order to maximize the production of hydrogen. So I'm showing the results for this plan, where they show an annual solar to fuel efficiency of 10%. The optical efficiency of the field was 46%, and the best temperature of operation were 2000 Celsius for the reduction, 1200 for the oxidation, and the annual production of hydrogen was 17.46 tons. Well, the size of this plant is 1 megawatt thermal. And then I took some data from the Solar Fuels Roadmap report, that data from sort of different processes in order to have an estimation of how much receiver and hydrogen production costs and the hydrogen safety will be. And I took all this data and do some calculations on the like system on the plant that I already optimized. And basically with all these sort of assumptions, a megawatt plant will cost about $1.5 million. If we want to calculate how much is going to be the hydrogen price to make that project attractive, with a net present value of 0.5 million and internal rate of return of 12, the hydrogen price should be $5 a kilogram, which is more than twice as high as compared to PV electrolysis system. The levelized cost of hydrogen, where this the net present value will be 0, is going to be above 3. Therefore, we need a CapEx reduction, or we need an improvement on the materials performance in order to make the system as cost effective as PV electricity. In this case, we had to lower the investment below $1 million a megawatt, and in that case, we can fit the LCOE, like the levelized cost of hydrogen, to $2 a kilogram. The selling price of hydrogen will be 2.29, and that plant performance will be much better. I reduced the receiver cost, hydrogen cost, and balance of plant by 50%, or also reducing the Elos-Staffel and design improvement quite significantly. This sort of cost performance can be obtained by increasing the production in 1.7-fold if we can find a material that can do that sort of production of hydrogen. So to summarize, we have presented today two different thermoeconomic models of one applied to compare different thermochemical energy storage system, and one applied to calculate the cost of a full plant of a solar thermochemical splitting light production hydrogen. And basically, most of the TCS cannot compete with molten salts, at least using the assumptions that I use in my work, that of course can be further improved. Also, molten salts are more simple to operate, and they are improving to be used at higher temperatures. Better thermoeconomics are needed in order to also consider for example, other plant designs. And for the solar thermochemical water splitting, the actual technology doing even improvements of how the system configuration could operate will require a significantly reduction on the CapEx to compete with other technologies. The system integration, I have to say that is quite challenging with the current design, so maybe other designs should be considered too. And a total CapEx will be attractive if we could have a lower than 1 million per megawatt thermal, and also having a lower LCOH or levelized cost of hydrogen if we can increase the efficiency by applying a novel material. So although the results are not very, let's say, satisfactory at the moment, I think there is a room for improvement. Thank you very much for your attention. I want to acknowledge the two research groups I'm working on, the Munich Lab and the ISU Lightworks, and also CSIRO Energy, because most of the work I did while I was still a postdoc at CSIRO. Thank you very much.
Thank you. Thank you, Alicia, for this very interesting presentation. And I would say there are maybe plenty rooms for improvement, not only one. So there are some questions, or even one?
Yes, that there is plenty of room for improvement. I think so too.
Yeah. Okay, this is an aspect we have to face with in any case, and this is I found that it's important to have also this kind of analysis during this meeting, because it will give us the possibility to think even over if it's possible with respect to our common work in the lab, at least. If there are no, Alfonso, okay.
Hi, Alicia. Thanks for this very interesting talk. My question is related to mixed oxides, or perovskites used for thermochemical heat storage. How easy or how difficult will be to implement that on your simulations?
Well, in the model that I did, probably not much. It depends if you want to account for just the heat of reaction, or you want to account for the heat of reaction plus sensible heat. It can be done as well. Yeah, it just depends on your assumptions, or what you will consider, like how much heat you will consider it come out of their system.
Okay, thanks. Great talk.
Okay. Other question? So if it's not, so we are going to conclude this nice meeting. So Emanuela, please.
Yes, thank you. Thank you so much, everybody, for making this meeting so interesting. And I know that very fruitful discussion came up also in the chat. So I'm really glad that we could meet virtually, even with this situation that is going on. I want to thank. I want to move to the acknowledgements to everybody. First of all, to the University of Messina. They really made possible to have this meeting, and which was open really to everybody. I want to thank Professor Milone for immediately supporting this idea when I talked to her, and for being the moderator of such great event. I want to thank all the speakers for accepting my invitation and trusting me and this organization. I know it's a busy time for everybody. It's been also a stressful period for many different reasons, from the personal point of view, but also from the personal one. So I truly appreciate all your kind efforts in participating. And a special thank goes from my side to Professor Aile and also to Dr. Coronado, who have been great mentors for my research project in the past 3 years. Thank you to all the participants, to all the attendees for making this a great debate. So I want to conclude saying that well, at the beginning, the initial idea was meeting face-to-face. But of course, because of the diffusion of this COVID pandemic, it was impossible to organize it. But we plan it in the future. And we plan it to also to cover different energy and environment related topic. I also really hope that in the future we can build a solid network, which would be really helpful for improving the career of young researchers, like I am, of course. And if any one of you is interested, I would like to propose to create maybe in a few months from now a roundtable for discussion. If we want to bring to a closer discussion, a closer meetings, and very more specific topics on the table. Maybe we can discuss about possible future collaborations. So I will send you maybe emails, and if you want, contact me, please. You can find my contacts on LinkedIn, on ResearchGate, and if not, well, I will leave also my personal email on the chat in the chat. And thank you again, everybody. I give the word to Professor Milone, and have a nice evening or rest of the day for you who are in the US.
Thank you very much to you.
Ciao. Thank you. Ciao, Stefania. Thank you to all of you. It's an interesting exchange. And I appreciate the idea, the Emanuela's idea about this roundtable. That I think it will be, it is a good path to continue in this exchange in mixing competence to drive the innovation real from the idea to the application. And we need all this mix of competence and this exchange continuously. So I hope it is really only the start for a long path. Thank you very much to all of you. Thank you.
Ciao. Bye bye.
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 Bye. Thank you.
Bye.
See you. Thank you a lot for the organization.
Thank you. Thank you for being here.
It's
really great, I have to say.
Really enjoyed.
Great thing.
Thank you.
Bye.
Thank you. Bye.
Bye.
salutiamo i ragazzi. Ok. Marco?
Io ci sono.
Ok, Peppe?
Sì, disattivo la riunione, la registrazione.
Ok, grazie per essere rimasti.